So I'm very pleased and very honored to be here. This has been a great week for me so far because I'm learning about a lot of really exciting research that's being done and a lot of excellent research that's being done. I'm going to try to tell you about some work that we're doing at PARC on a thing we call content-centric networking. It's being done by a large group at PARC. The head of the effort is Jim Thornton, and the second lead is Diana Smetters. She's primarily doing the security architecture for it, but also almost all the other pieces. This is the largest single project at PARC. I'm using up almost all of their internal R&D funding, for which I'm embarrassed. And in this whole group of people, I am far and away the least productive, right? The rule is you can either talk about stuff or do stuff, and I'm the one that talks about stuff. We have very ambitious goals. We want to do a brand new communication architecture. We would like it to work as well as the internet. The goal is not to replace the internet, it's to evolve, to take another step. And the motivation for it is the internet changed the world, and it was designed for the world of an earlier time. And we can see the cracks because it doesn't fit the world that we have today. We would like to do something that's a better fit. And we think it's pretty clear what the general outline of that better fit is. But we need to make sure that you're not taking a step backwards, that it has to work at least as well as TCP/IP in every dimension. Some of the places where there's real pain in the current internet, particularly in security, you want to fix that. Security has to be far more fundamental. And just hooking up the current internet, getting things to work at the internet level and at the application level that runs over it, that's gotten to be very hard, much harder than it should have been. We think that that's due to a model conflict. It's that the problems that you want to solve and the way that you have to solve them are no longer very close. And because of that, you have to put in a translation layer. We looked at programs, the various elements of programs 5 or 6 years ago, and we're finding that increasingly they were middleware. That you'd have an application layer that was fairly slim, you'd have a network layer that was sockets, it was fairly slim, and you'd have a huge chunk of goop in the middle that was translating between the applications model of the world, which was generally content-focused, and the networks model of the world, which was host-focused. And that's a very hard translation because they're fundamentally different. Thought that if you had a network that worked more in the applications world, then all that middleware could go away. You don't have to translate between models because they're the same model. On the road to doing that, hopefully you're doing something useful and you're doing a universal middleware. You're doing a networking infrastructure, something that's designed for communication, but it works in the application content model. And it overlays on top of IP, but you do the translation once in one way. And if you can do that, you get a nice evolutionary story, sort of the same story as the internet. The original internet rollout was 4 nodes, UCLA, Salt Lake, SRI, Berkeley. You demonstrate the communications protocols running between those nodes. Say, okay, it works, it can talk. You have other computers in your campus and you say, well, the virtue of this network is it concatenates networks. That's how Vint originally named the internet Catanet, and it stood for concatenating networks. And it was designed to be an overlay that abstracted out the behavior of the lower level networks, these things that today we call layer 2, in a uniform way so that you could glue the pieces together and it would provide transitivity. And that meant that you could grow networks without thinking about translating between the different protocols, because the translation was done once in the IP layer, in the shim layer. And what that meant was, at a time of a lot of evolving technologies, long area modem links that were getting slowly faster from 9600 bits per second through 56 to 128 to T1. The newly invented Ethernet that was giving us 3 megabit per second connectivity and then evolving to 10, and then lots of experimental wireless links that were being used for digital military communications. Those were all networks that worked in isolation, but we wanted them to work together, and we wanted them to work together without having to do a lot of human configuration work. And the internet gave you that. So when UCLA buys a bunch of computers and pops them down in the computer room, and they want to hook them up to this internet test infrastructure that they had, they put TCP/IP on them, and they did an Ethernet driver. And suddenly all those computers could not only talk to one another, but they could talk to the computers at Berkeley and SRI, because these dissimilar networks concatenated, they joined together. And that was done by the machines. It was the objective of the protocols to provide that concatenation. And so people didn't have to think about them. And that was completely revolutionary. All networks up to that time, you had to manually hook them up. You had to manually configure them to make them work. And to have a network that hooked up itself was tremendous value. It meant many, many more people could start to do networking. And that caused the internet to grow inside of campuses, because now all you had to do was buy the machines and the internet hooked them up for you. And so you get these little viral clouds of the internet growing in lots of different institutions. And then the NSF gets a bright idea of putting a wire between those institutions, and suddenly we had a big national network. And it didn't require any work. And at every step, it presented some value. We would really like it if future internet technology, maybe a content-focused technology, could grow in the same viral way, that you have a little limited deployment and it provides value, maybe value as middleware. It just makes your applications work better, work more seamlessly, and you don't have to think about the configuration and hooking things up. But over time, as the islands grow, they start to concatenate together, and pretty soon you have an entire network that works as in a content-focused way, and you start to ignore the lower layers, and they start to wither and go away. So that was the word universal in our description of CCN. Now, anytime you're doing a communications architecture that works over anything, it's necessarily an overlay. I mean, that's the way you say works over anything. You overlay, I don't care what's underneath me. So because of that, overlay is not a useful distinction, but the expressibility of the thing, that is a useful distinction. You started out with IP as a pure overlay on the phone network. And there were people that said, IP is not a network, right? It's the phone system is what provides the connectivity, it's what provides the networking, and IP is just wasting a bunch of bits with headers. Well, starting in 2003, things flipped. In 2003, the amount of phone traffic that was carried in packets had been steadily growing. By 2003, the majority of the world's phone traffic, 80%, was carried in packets, an IP packet over SONET, because it scaled. And the phone service turned into largely an edge service. You packetize, then you distribute via IP. So we went from IP overlaid on phones to phone system overlaid in IP. Took about 40 years, but it shows you something of the expressibility of the IP network, that not only can you overlay anything, overlay it on anything, but you can overlay almost anything on it. So we intend the work on CCN to have the same character. It's a universal overlay. It's more expressive than IP, so it's easier to overlay it on top of other things because it puts much less demand on the lower layers. IP really requires a point-to-point abstraction in the lower layer, and it really dislikes broadcast links and links that don't have addresses. CCN loves them, I mean, because it doesn't talk to things, it talks about things. And so you can overlay it on pretty much any communication link we've got. You can overlay it on IP, which means you can deploy it now as middleware, but you can also embed IP in CCN. You can run IP quite easily over CCN. You waste a little bit of space because the CCN headers are bigger, but the functionality is as complete. So here's the plan for what I'm going to talk about. A little bit of history and motivation for why CCN. To describe it, it's really hard. I've given talks on many talks on CCN. They're mostly failures because you need two different ideas in your head, and having only one of the two, it looks pretty nonsensical. One is a different model of forwarding, a different model of the moving parts of the network, because it's a network that doesn't talk to things. There is no host abstraction. There's only a content abstraction. And that makes some surprising differences in the forwarding machinery. It's as simple as the IP moving parts, but they're different moving parts. But they apply to a particular content model. And it's in the same way that you read RFC 791, the description of IP, and then you say, okay, this moves packets around, but how do I really get a job done? I've got this file and I want to move it from here to there. How do I do that? That's not in 791. That's a transport problem. About TCP, and then it's all pretty clear. But until you read TCP, a lot of the things that are done in IP seem silly or pointless, particularly if you come from a background of, say, X25, which is a different model of what the underlying network is. Not only does it seem silly and pointless, it seems like it's not going to work because it doesn't provide the basic capabilities that you need for that model of transport. So we've got the same issues talking about CCN. You have to understand its transport model, but unlike TCP, where you're trying to move a byte stream, in CCN, you're trying to move a fairly rich object space. And so you can't really understand what you're trying to accomplish with the moving parts until you understand the content model. And it's very hard to pick an order that works for describing these two things, because I can't talk about them both at once. So keep an open mind. I'm going to start with the content model, and don't check out and say, boy, this is really dumb, before we get through the moving parts. And you can see how that content model meshes with the machinery. And at that point, you're free to say, this is really dumb, or that will never work. From that point, we're going to go on to how you do routing when you've only got content, how you do transport when you've only got content, with a few examples and some measurements that we've done on our prototype implementation. So, launching into the history. This is what the world looked like when the internet was invented. It was a very different world. There were only a few computers. They generally weren't connected to anything. If they were connected to anything, it was one connection. Everything about these computers was expensive. They lived in little glass-enclosed rooms, and they had a whole cadre of priests that attended their every need. Normal users couldn't go in and deal with the computer. When I was a physics grad student, and when I wanted to run a program, I handed my tapes and card deck to an operator who would take them in and feed them to the computer, and they'd give me back my printout and hopefully give me back my program and tapes. But it was a world where what was important was keeping the machines busy because they were so expensive, and having the resources available to this expensive machine so that it could do its job. And there were a lot of resources that you needed: card readers, punches, tape drives, printers, and all of them were fabulously expensive by today's standards. A printer cost as much as a house. So what you were mainly interested in was sharing these resources. If you had a communication link, you said, maybe I don't have to buy 2 printers, maybe I can buy one and use it on 2 computers. So the goal of the networking protocols, the reason they came into existence, was so that you could share resources between computers. The goal was not about sharing data. In these days, data didn't live on computers. It lived on tapes and in card decks. I mean, that's my thesis data and the cards that my thesis program was written on. I carried it around with me. It didn't live on a computer. Networking today, right, we don't think about sharing resources. Computers are disposable commodities. This laptop's got more than a dozen computers in it. My phone has 8, right? They're everywhere, they're ubiquitous. Nothing about them is particularly expensive because the economies of manufacturing have gotten so large. What happened in the intervening times was largely through networking, we created this brand new world of content where the computers aren't important, but the data that's on them pretty much defines our lives. And this is bad because the networking that we did, because of the times, put its central abstraction as the computer, this thing that we no longer care about. And because we were interested in sharing resources, what those abstractions did was have a conversation. You wanted to extend the I/O bus because that's what the resources were about. You want to talk to your printer, talk to a tape drive, and you wanted to talk over this network connection. So you had primarily point-to-point conversations between exactly 2 hosts. So what does that mean today? Well, everything about today's world networking hates. It doesn't like mobility, doesn't like things to move around because its model is 2 fixed points that are having a conversation. It doesn't like intermittent connectivity, and that's another instance of things moving around. As we're writing applications, since there's so much content in the world, your mindset is, what information do I need? What information do I want to present? We work in a world of content abstractions. When you actually need to move information around, you've got to change that into host abstractions. Who do I talk to in order to get the data I want? So the second question you ask after you figure out what your app is supposed to do is, okay, where's the server? You have to bind the who in order to make the what work. And you end up doing that largely through configuration. I mean, the apps really just care about what, but you have to change the abstractions, and because there's no relationship between them, you can't algorithmically derive where the data is from what the data is. You need to put in some manual configuration or some configuration infrastructure in order to tie things together. And that's this huge growth of middleware and this huge growth in non-functioning networks because they're easy to misconfigure. And lastly, the value of this resource sharing network was to provide a bit pipe. It was to move bits that were completely opaque to the network from one machine to another. And to the extent that you could keep the data completely opaque, you really didn't care what was there, the more devices you could support, the bigger range of conversations. And this is goodness. But what it means is the network has no visibility into those bits at all. It has no concept of what you're doing over that wire. And what that means is when you talk about security at the network level, what it can do is armor the wire, because that's all it knows about. So it can make sure that the bits in transit don't get corrupted. I don't care that the bits in transit didn't corrupted. I care that the bits I get are the bits that I wanted to get. They're from the person they purport to be from my bank and not from some scammer, that there was nothing added or deleted. Well, the network can't guarantee that. It can't see the content, can't help you with that problem. And yet you see a lock on your browser that says, oh, SSL, this connection is secured. Well, it's not, right? The security in the human terms is completely invisible to the network. And that's the function of, that's deliberate. That comes from the fact that the connections, the content is opaque. So today, all we do with the net is move around content. Andy Olitzko, originally at Bell Labs, now at University of Minnesota, runs a measurement program called MINT. And the last data he published on his website was he's measuring the internet moving 8 exabytes a month at the end of 2008. So that's, if you work out that amount of data and the number of seconds in a month, that's 25 terabits per second, 24/7, right? Every second of the day for that entire month, you're moving 25 terabits, which is interesting. We finally filled a fiber, right? That's really close to the theoretical capacity of a fiber, and it's taken us a long time to get there. All that data is not just shuffling around the stuff that already exists. We're producing it at a prodigious rate, particularly since all our new devices can automatically upload video to YouTube, right? There's a huge content creation explosion. Company called IDC did a study in 2008. When you get the slides, those things at the bottom are links. That's a link to the study. They found in 2006, there was 180 exabytes of brand new content, of original content produced in that year. So most of that 8 exabytes a month is new stuff that's being made. And they've been doing this study every year for about a decade. And what they found over 10 years is 60% annual growth. So their projections are more than a zettabyte by 2010, by next year. These are, so a zettabyte is 10 to the 21st, right? And we're running out of letters in the alphabet for the size of content. These are just unimaginable amounts of data, trillions of terabytes of data. The thing that's driving that is the evolution of the cost of storage. So this is data from Thompson at IBM. He did a survey article in IBM Journal of Research and Development about the dollars per byte of IBM disks at the time that they were introduced. And he looked over 20 years. I published 10 years, or I graphed 10 years of that data. So, and that's a log linear scale. It's an exponential decrease. There's another set of data that comes from Doug Galby, who was chief economist at the US FCC until Bush seized power. And he was surveying carrier prices. When Bush took power, all of that data vanished. And he published, I picked one, OC3 prices over the same time period. And that's this axis. It's also a log axis, but it doesn't need to be. And it's for an OC3, it's the dollars per megabit per mile. So one's an exponential decrease, the other is flat. And I generally get grief about this graph because we all know that communications costs have been going down. They haven't been going down anything like that fast. And there's actually useful data here about how telcos work. So in 1990, the first point of that graph, the US was just making a transition at the customer level from copper TDM infrastructure to optical infrastructure. Internally, the network had changed to be largely all optical, but the tails going out to customers, what you could buy was all copper. Fastest you could get was a T3. And then suddenly around 1990, you began to buy faster things, these 150 megabit OC3s on fiber. So you get a relatively high price at a new introduction, but the way it was sold is, hey, I'll give you 3 times the bandwidth at only twice the price. So actually your price per bit is going down. And they got people to dump their old T3s and put in OC3s. And so they could retire this very inefficient, expensive copper infrastructure. At the end of this period, 2000, the internal backbones had all been upgraded to OC48. They were OC12 at the beginning of the period, and they were moving to OC192. And multiplexing is really expensive. The less muxing you have to do for a customer, the cheaper your costs are internally. So there was a lot of advantage to the telcos to push OC12s out to the customers rather than a bunch of OC3s. So because they had a much fatter backbone, they were offering higher speed links at the edge to customers, and it was the same deal. Hey, I'll sell you this OC12, 4 times the bandwidth and only twice the price. Huge deal. So your costs have gone down by a factor of 2. Telco costs go down by a lot more because an OC3 actually costs them more than the OC12. But that's why that line is flat. Is if you look at one technology as opposed to the average cost per byte, then the way that the telco business model works is there's a lot of inertia, and there's a lot of inertia no matter what. Right? There's just no way, given technical constraints, financial constraints, regulatory constraints, that they can drive their costs the way that this can drive their costs. But the disk cost, that decrease is staggering. Right? It's been falling 3% per week, every week, for the last 25 years. And if anything, if you look at recent times, it's falling faster. Right? There are new recording technologies. And if you try to look in the future, that curve is likely to accelerate. And the reason is, the one thing that nanotech does really, really well is produce large regular structures. And just in the last couple of years, we've seen a whole bunch of wonderful things coming out of labs that are all big regular structures that function as memories. So in 2008, Max Planck Institute showed this self-assembling nanocapacitor array, nanotech fabrication. The PZT ceramic that they used for it is something that you use to coat pots. Right? So it's just dirt cheap. It's 200 gigabits per second is the minimum density. They're first cut out the gate. That's state-of-the-art disk density. That's how much density you can get on a platter in a lab. And it's way beyond what you can buy today on the market. This month, University of Twente announced this MEMS array. Standard silicon fabrication techniques, you're storing bits in this mechanical structure, flipping little gates around. 4 terabits per square inch. All right, 50 times the best that you can do in disks, and it requires no power to run, is completely non-volatile. In February, LBL announced this self-assembling copolymer structure, 10 terabits per square inch. They also announced this really cool thing where they were taking carbon nanotubes and embedding a magnetic particle inside of them. And then you could apply a field to move the particle to one end or the other of the tube. It's only a terabit per square inch, but because you completely seal the particle in its own little environment in this tube, there's no way to disturb the state of the bit. So they get a per bit lifetime of 1 trillion years. It's the first electronic technology that we've ever made that has a longer lifetime than stone chiseled tablets. Right? It could really survive for quite a while. All of these things are happening. They're all really cheap. They're all storage. Right? Because there's a lot of demand for storage because of this content creation cycle. There's a lot of technology to produce these very fine structures, and we're scaling them down to the atomic level. So the densities are just shooting up. Given these trends, both the bandwidth trend, where it just can't evolve very fast, and the storage trend, where it's just evolving like lightning, you would really like to be able to trade storage for bandwidth. Right? Whenever you have to pull bits across a wire, you're going to end up paying a whole lot more. There's a problem with this. In storage and communication work in completely different worlds. The storage world is what you want. The way you get a file is you present a name and you get back the bits that are associated with that file. The way that you get a file over the network is you find a server and then you talk to the server and you ask it to give you the file. So the primary thing in a communication problem is who you talk to. In a storage problem, it's what you want. And that's the model conflict. It means that these two don't substitute very well. So an interesting question is, the abstraction that we picked in networking wasn't God-given, right? It's not the only way to do it. It's a thing that was the right thing to do at the time that it was done, in the 1960s. It's not the 1960s. Can we do a network that has the properties of the internet, same scalability, same performance, same robust operation, but we change the abstraction. We make the abstraction be a content abstraction. And that's the main change, but it's got some consequences. So, yes, of course we could do that. I wouldn't be here talking to you if I didn't think we could. Here's a model of how you might do that at a 50,000-foot level. The example of this one is data that I really want to move around all by itself. I want it to manage itself, which is my calendar, which, you know, it gets updated on my phone, it gets updated on my laptop, it gets updated on my home machine, it gets updated on my work machine. My wife is always putting things on it, and I absolutely have to do all of those things. Because it's sort of this distributed set of data, there's no object I own that has a consistent view of my calendar, and I'm always forgetting to do things that I absolutely have to do. I would really like it to run itself, so here's a model for that. I tell my phone that it's interested in my calendar. I tell my desktop that it's interested in my calendar. I walk into work with my phone. My phone is broadcasting over all its interfaces. It's got a Bluetooth, it's got an 802.11. It's saying, anything new on Van's calendar? I'm interested in Van's calendar. I get to work, the desktop hears it and says, oh, I have something for Van's calendar, you have a pointless meeting. And it supplies that to the phone. So, basic model is devices are saying at a high level what data they're interested in, and other devices hear those interests, they compare it to the data they've got and say, I've got one of those, they can respond. I leave work, I go home, my laptop at home is playing the same game, it's saying anything in Van's calendar. The phone says, yep, you had a pointless meeting. All of those devices end up in sync. I didn't tell my phone about my desktop. I didn't say, here, query the desktop to see if it's got new calendar entries. Query the laptop to see if it's got new calendar entries. That's an n-squared problem. I have to introduce all the devices and make them, and do the plumbing. Right? Now I want to work at a much higher level. I want to tell the device, keep track of my calendar, make it so, right? Don't bother me. And they manage the details. So this model, they do manage the details. And in this model, I'm the network. I'm the one that moved this calendar entry from work to home. I moved it in the memory of the phone. Right? It doesn't matter what the communication vehicle is. If it moves bits, it's a network. It moves bits. So here's trying to say that last thing in words. The user gets to work at a higher level. They specify the objective, not how it's accomplished. The devices deal with how to accomplish it. The data appears wherever there's interest in it. So it manages itself. It goes where it's wanted. It doesn't go anywhere else. It's a model that loves broadcast because it's not talking to things, it's talking about things. It's asking questions. Do you have the calendar? It's like asking, does anybody have the time? Right? I don't need to be introduced to each of you to ask that question. I can ask it of the room, and I can get a good answer back of the time. We're at that same level. Right? We work at the data names, not at the participants' names. We're asking by name, so the difference between communicating to storage and communicating over a wire goes away. We treat them exactly the same way. They're the same abstraction at the networking level, at the communication level. And this is an assertion. I haven't proved this or in any way demonstrated it. But if you're going to do this, then you have to make data integrity and security your first job rather than your last job. And it's because right now we pretend that you can get security by armoring a wire and by making a trusted perimeter around machines. It's false, you can't do that. But we pretend that it's true. And sometimes it works. It slows down the attackers a little bit sometimes. When you're doing wireless, that's a fantasy that's just not supported, right? Because you don't know what's talking to you. It's wireless, right? There's no connection. And the source of that RF could be anything. This is the first thing that telcos learned when they went from landlines to mobiles, right? If you've got a landline, you know exactly where to send the bill. You send the bill to the house that the wires are attached to. Right? You've defined a location by the physical attachment to the network. I carry around my cell phone. Right? What's attached to it? Nothing. It's a cell phone. Where's the bill go? That's really important. Because I don't have a physical connection that I can use as some source of identity or some identification of the service, the only thing I've got is the data. So right after you invent the cell phone, you invent the SIM chip. And you have to give some cryptographic assurance of the identity of the subscriber. If you can't get identity out of the wires, you've got to get it out of the data because there's nothing else, particularly in wireless. There's just the data. And because of that, you think about security because it's fundamental to doing any service. And that's a segue to the content model. So, given the growth of information, we need to make it self-managing. Right? If we're going to get zettabytes of data, it had better mostly manage itself because we don't have time. Right? Nobody lives long enough to deal with that much data. The sun won't live long enough to deal with that much data if you have to handle it bit by bit. It's got to mostly be automatic. It's got to mostly be run by the devices themselves. If you want it to self-manage, if you want to delegate the work, like delegating the calendar sync, then the things you delegate to need context, or they're going to screw up. And the context is three kinds. They have to be able to identify the information that they're going to work on. That's ontological context. Right? Calendar sync, you have to know what spans calendar. And you have to make sure that you don't sync other stuff. And other stuff is two kinds. You don't want to sync non-calendar stuff, like you don't want HD videos to move over to that cell phone. And you don't want the data to flow places that aren't VAN. There's two important aspects of the ontology. One is calendar and the other is VAN, my stuff, going to my devices. There's a privacy aspect for things like calendars and much other information. The provenance of the information. In this communication, we don't know who we're talking to. We don't know who's supplying it. We deliberately don't know. We don't care. We care about the information. But if you do that, you need provenance in the information. Who created this? Right. Something attests that it's an item for Van's calendar. I mean, just because it says it, is that true? Probably not. You know, there's a lot of spammers. There's a lot of bad guys in the world. You don't get much by forging an entry to my calendar, but there are other forgeries that would get you revenue, like forging a charge on my bank account, and those are electronic transactions as well. So I need some basis for trust in the information, and it has to be in the information, because all I've got's the information. It's just the bits. And lastly, what I do depends on where I am. And the things I try to do depend on where I am. When the internet was designed, it deliberately didn't include locality. You can't tell whether you're talking to something adjacent to you or something across the world. And that was by design. It was a good design. But if I'm trying to move my videos from my camera to my media server, I don't try it while I'm here because I don't have any viable connection, any way to talk to my home video server, and it would be fabulously expensive if I even tried. I would like to know what the local context is before I start to do anything. It's going to condition what I'm going to do. And I want to make my agents aware of that. And there's another set of issues. So you're trying to automate things. You're trying to get things to be done on your behalf. You're trying to work at a higher level so that by you taking a fairly simple action, lots of complicated actions happen. So you're making amplifiers. But amplifiers, you know, there's this old saying that it's a poor gun doesn't point both ways. You can always shoot yourself. And an amplifier can amplify bad as well as good. You need to make sure that you engineer that out to the extent that you can. And that can be hard. So it's easy to make mistakes, particularly when you're moving data around. So there's a really popular file sharing device called folder share. Presents the abstraction of a single file folder that exists on an arbitrary number of machines. If you take a file in folder share and you delete it, and it's one of those oops moments where, oh, I didn't really mean to get rid of that one. Well, folder share doesn't know that, and when you delete the file, it makes sure it gets deleted everywhere. So all your backups vanish as well. You don't want to do that. I mean, you really don't want to amplify that mistake because that's a really common mistake. And in the world we live in today, there's unfortunately a lot of bad guys. They've realized that there's a lot of money flowing over the internet, and they want that money. And there are a lot of different ways of attacking us from the net and via the net. When we're amplifying our actions, we don't want to amplify their actions. You don't want to amplify attacks. Right now, the attackers, because of our packet forwarding model, the point-to-point model with transparent data flows, as what's called a gravity model. It looks like you've got a sink, you've got a bunch of pipes connected to it, and the data has to run down because you can't look at the data and figure out if you've seen it before, right? It's opaque to you. So you have to make sure that all of the pipes go in a downward direction and none of them have any loops. And that's the topology maintenance problem. It's why we run routing protocols. We have to make a sync tree and we distribute data over it. And the root node of that tree is the destination of the data. There's one path from any source to that destination. But another way of looking at that is the sync tree is a lens that attackers can use to focus traffic on the destination. This is the basis of all the DDoS attacks, that you can have a zillion zombies that you recruit from Microsoft's Chromium Secure operating system. You run a little program on that, sends a little bit of traffic, but if you do that from 100,000 machines, you can blow anything out of the water. You can blow Google out of the water. And because the lens only works one way, it's asymmetric, all the advantage is on the attacker's side. It's very hard to remediate that attack. It's hard to push back towards the attacker because the net's just doing its job. It's focusing traffic, it's collecting it, it's delivering it to the destination. There was an engineering choice that was made there that was a consequence of other engineering choices. Right? You have to make the lens. It comes from the data transparency in the protocol. Maybe we don't have to do that if we change our model. Maybe we could make it harder for the attackers and easier for the defenders if we move to a content model. I'm looking at where I've gotten to in the presentation and I need to talk a lot faster, so I will start to do that. Here's roughly where we left off. So if You want to self-manage the information, you need these three things, and you don't need friction. So how do we deal with that? First, we jettison the host abstraction. It gets in our way and it provides no value. The way that you usually get ontology is via hierarchy. You get meaning by organizing your knowledge in a structure, hierarchical structures typically. We do that, and they're represented as hierarchical names. The provenance we get via signing. It's the cryptographic primitive for giving provenance, for establishing identity or asserting identity. And a particular type of signing. What you want to sign is not the name, and it's not the data, it's the binding between them. That's what's important. And I need to give an example of this. So in the last 8 years in the US, we learned a lot about lying. And there are two styles. There's a Cheney-Bush lie where you just make something up and say it, right? Just corrupt data. If you sign the data, if you have self-certifying data, you can detect that kind of lie. But there's another style, there's a Rumsfeld-style lie, where you give a true answer to a question, but not to the question that was asked. So somebody says, are there really weapons of mass destruction? And you say, yes, I had oatmeal for breakfast. That's harder to detect, right? If you just have self-certifying data, it certifies, but it's totally irrelevant. And the only way that you can establish relevance is by looking at meaning in context. And it's the ontology, it's the name that gives you the context. And so if you want to prevent that kind of attack, which is the very common kind of attack because it works so well, you need to certify bindings, not just the data, not just the names. So that's how we generate provenance, signing everything. And the way that you get locality is you make visible at the network layer the way that bits flow. Bits diffuse from a producer to a consumer. That's the way the network works. Right? We can't teleport them. They have to move. But since the early days of telephony, we try to pretend that's not happening. When you're talking to a telephone, you view yourself as talking to the person on the other end. You're not. You're talking to the phone. Right? And then there's some complicated electrical things that are happening, and your conversation is diffusing through a network and is being reproduced on the other end. But you're talking to something local. When you're communicating to something local. If you make that explicit, if you say, hey, that's the way it works and I'm not going to try to hide it from you, then you can use that locality as part of your engineering. You can make that awareness both part of your protocols and you can expose it higher up in the stack. So we don't try to abstract that out. We use a diffusion model. And the way that you get rid of friction is you correct a mistake that John von Neumann made, which is thinking of information in terms of its containers. And I want to talk at some length about that. And it's on this theme. Security on the internet is really bad. It just totally sucks. And that's not because of sloppy programming, though there's a lot of sloppy programming. It's far more fundamental than that. It's because the way that we view information is not the information itself. Right? We can't name information. What we can name is where it lives. We can name its containers. So when you get a web page, you get it from a host, right? That's a container for a bunch of web pages, and you get it from a file on that host. In your mind, that's what you're referencing. You hope that the bits in that container are what they're supposed to be. When I reference a web page on my bank, I really hope that they put those bits there, and it's the bits that they intended to be there. But I have no assurance of that, and they have no assurance of that. Right? It's very hard to know what's in a container, but it's the basis of computing going back to the very early days, and that was the world that I showed you in the 60s and even earlier in the 50s. Machines were very expensive, memories were tiny, so disks were kilobytes. My first computer had 4 kilobytes of serial delay line memory. It was a serial machine in the early 1960s. And that was a lot for the time. It actually had a Fortran compiler on it, in addition to the normal utilities. You could do that when you had whole 4 kilobytes of memory to deal with. And it didn't have a disk, it had a paper tape reader, which would accommodate, I think, 12 kilobytes on a spool of tape. These were the size of memories that we had. It's one reason why data didn't live on machines. And because of that, when you wrote programs, you viewed your data as coming from some external source, which you abstracted, the tape drive, or staging the data into a file on the disk, and so you would read from input, which is a container where you dumped your data, and you'd write to output, which was another container where you'd put your results. But you never dealt with the data directly. You never named it directly. You couldn't, because you had to keep replacing it because all the storage that you had available was tiny, right down to the machine level. We didn't have a lot of high-speed memory. So machines had registers, 4 or 8 locations of high-speed storage, and you did computations in the registers, and then you had this much slower RAM, which was little ferrite cores, where you'd store the results and you pick up new computations. Right? So we got into this mindset of naming the containers to operate on their contents. But that's totally insecure. Right? You can't know what's in a container. And for many years, for decades, both John Bacchus of IBM and Tony Hoare, now of Microsoft Research, got the ACM Turing Awards for preaching against containers. They say it's the source of all bugs. You really don't know what's in that container. Even if you try and track its history, if you've got any sort of parallel processing going on, something can overwrite it. For security properties, even though you elaborately seal it, Ron Rivas gives a talk about the fallacy of the unpickable lock. He says, a lock by its nature has to be opened. If it can't be opened, it's useless. Right? You might as well weld whatever's locking shut. But if the lock can be opened, it can be opened by good guys and bad guys. Right? Lockpicks work just as well as keys. There's a whole class at MIT on lockpicking, because a container, by its nature, you need to be able to replace its contents. If you can't do that, it doesn't fulfill its mission. But if you can replace its contents, the bad guys can replace its contents. If you look at all of the attacks that are currently extant on the internet, they have to do with attacking containers. The most common ones being things like cross-site scripting, which is make a container, make a web page, point somewhere other than the user thinks it points. But you can attack many other kinds of containers. You attack the host container by attacking ARP so that you get the MAC layer to IP address binding, by attacking routing so that you get divert the path binding, you route your data through somewhere else, attack DNS by attacking the name to address bindings. All of these things are levels of indirections, ways of doing containers, moving you away from the data that are easy for attackers to circumvent. If you want to really secure data, you secure the data, not the thing that holds it. And that's easy to do, right? The containers are another thing that was not God-given. If you develop any sort of code, you probably use some version control system, Subversion, CVS, Git. There, they say, I don't want a file container because I'm sitting there hacking on something, chugging along for an hour, and I go, oh, damn, that's never going to work. I want to back up and start over again. Well, if I had a container, where I was is gone. What I've got is the hour of mistakes that I've been making. If I've got a version control system, not a container, then it's keeping the whole temporal history. I see myself as working on files, that's what my editor sees, but in reality, I'm working on this tree-structured set of information which captures all of the versions, and I can go back in time, and I frequently need to do that. And it's a model that presents itself as a container, but it's a lot like if you're doing compiler work you know the first thing that you have to do to transform program into code or into some form that you can optimize it is go away from the assignment form, the A equals A plus 1 form, into an SSA form, a static single assignment, where you distinguish the two values of A, the one before the modification, the one after. You give them two different names. So that's adding some temporal annotation to the container to turn it into the name of data, not what it contains. So there's easy ways to go away from the container model while still preserving the illusion of containers, letting users deal with names like containers, and they can only dig into the details, see the temporal evolution if they need to, like they need to roll back in time. And if you do that, if you move away from a container model and start talking about the content itself, then you get something that's really easy to secure. You can secure the actual content by signing it. And we've known how to do that for 2 decades in ways that are absolutely unbreakable. Nobody can tamper with that content and not modify it, not make the signature invalid. We do that, we make it immutable. So that is, we have a collection which are the versions of that content over time, and each one of those can be signed, and so the integrity of each one of those can be assessed. So that's what we do in CCN. You get rid of containers. What a CCN name names is a collection of data. This is our content model. So we're not ever naming a repository of data. We're naming a set of data. That set may have a single item in it, a single data value, may have multiple items in it. Anybody can add to the collection. The set is defined by the naming structure. So the set of all items, the collection is a set of items with the same prefix. We have this hierarchical name structure. And there's no single system of meaning. You can't ever describe an ontology or a hierarchy that captures all meanings, captures every way that you want to represent your data. But the web gave us an easy way to deal with that. You put in links. And in general, you want to put in symlinks, right? So you have a name whose value is another name, and that connects one view of data, one way of naming, with another view of data. It can connect anywhere in the tree, so that you can turn your ontology tree into an arbitrary graph. Okay. I want to make that more concrete. So here's an example of a name for that calendar application. So the prefix up there, park.com, van, cal, so that's the collection of all my calendar items. I'm at park, so they gave me a prefix under their prefix, right? A place to make names. One of the things I want to name is calendar items. The particular one that I was dealing with, that pointless meeting, could be some vCard file for my card application. It's evolving over time because all those meetings seem to move around so that they can sort of do the maximum damage to your day. So this is version 3 of that meeting because it's been moving around a lot. So that part of the name captures the temporal evolution. You deal with things that are all different sizes in the world, but you don't want the network to deal with things that are all different sizes, right? The smaller the unit you can put on the network, whatever the maximum size unit, that's the granularity of sharing. And if you put really big units on there, you're not going to share very efficiently. And you can either, between the objects in the network, you can put some fragmentation protocol, that's the model of TCP, or you can say, if I can name collections, which I need to do, then a collection of fragments is a collection. And I don't need another namespace in order to bust things up into pieces. I just name the pieces. And so you get some parsimony and you get some very nice things happening at the protocol level that I'm going to talk about later. So that S0 says this is segment 0. It's the first piece of whatever this item is. This item only has one piece. And then the last is either the content or a proxy for the content. It's currently using SHA-256 checksums. So if you want to name right down to the content level, these bits and no other bits, right? So this calendar item, as it was on today, July 22nd, I can name those bits. I can make a link that points to those bits. Can't be forged. It's always going to resolve to them, no matter how this entry is changed, right? Because I put the bits in the name. It's a proxy for the bits, right? It's a finite length proxy, but it's unforgeable because it's a one-way checksum. If I'm replying with the data, I can compute that proxy from the actual data, so I don't have to put it in the name when I'm returning the data, and it can still be validated. But this is, names of this form is how you validate the binding between the name and the data. You essentially put the data in the name. And this is another idea of Ron Rivas. It came from a system that he did called SUDSI that I'm going to talk about in a little bit. Thing to say about this is the binding that we're doing here is immutable. Right? So I can make other objects like this, but they're new objects. If I change the calendar entry, I've changed its name, because if nothing else, I've changed the bits on the end. And I may remember to change the version number, I may not, but I've made a new item if I change any part of this. Right? So because of that, I don't have the coherency problem that I do if I'm talking about containers. Right? Whenever you try to replicate content, when you have a container model of the world, you have to make your replicas consistent with the master copy that lives in a container somewhere, that lives on some machine that defines the content. We don't have locations for content. The content itself authenticates itself and identifies itself, no matter where it is. And you don't have to be consistent with any other copy. You have to be able to validate this copy. This is a legitimate copy of version 3. You can check the signature and make sure that's true. What that means is when you're doing coherence protocols, there's nothing that can happen that can make what you know wrong. Right? Nobody can change this version underneath me. They can create a new one, so they can make my knowledge incomplete, but they can't make what I know wrong. And that completely changes the operation of the replication, the consistency, and the coherence protocols. And there's some great work, system called Practi that's been done at UT Austin, where they teased apart the replication of data from the storage of data, from the containers of data, and said, if you could name the data, then you could give independent control of the replication and the coherence semantics. And you can do more than give independent control. Each receiver can choose the coherence model that's appropriate for that receiver, which means that a lot of the consequences of coherence, which are serial consistency, which forces you to do things really, really slow in a distributed system, you can make that go away, because your backup program doesn't need to be serially consistent, it just needs all the data. Right? And because you've decoupled the semantics of consistency, you're not dependent on a container, you're just dependent on getting all the data, you can use a system like Practi to make the consistency and coherence be receiver specific. It means that you can choose to operate in a lot of different performance regimes, and by default, you work in a very parallel, very high performance regime. Provenance, I've waved my hands about signing. Here's some more details on signing. So you take that whole name, which includes the content on it, and the thing that created that data, the last thing it does, my calendar program, the very last thing it does is it signs the whole thing, and then it injects it into the network. That's done at the bottom of the app, right? The app's interface to the network stack. It's not done at the kernel. And the reason for that is to make the attack surface as small as possible. The creator of the data, as close to the creator as you can possibly get, that entity signs the data. It seals it, attests to its integrity. And nothing after that point modifies it. Within CCN, IP packets get rewritten at every hop. They have to be so that you can update the TTL. In CCN, packets are never modified. And if they are modified, you can tell. So the program that created that signed the data, it had a signing key. That was its key. And in the packet, there's a key locator, something that points off to the key. The key can live in the packet. It can be a pointer to the key somewhere else. Generally, it's the name of the key. And in general, it's a rule that tells you how to go from the name of the data to the name of the key. A very nice thing about going to a content-oriented model where you actually name the data is you don't have a key distribution problem, which is the Achilles heel of all security systems. If you've got a container view of information and an armored pipe view of the way that information flows around, there's no way to associate the key for a set of data with the data itself because you don't have a name for the data itself. Right? You're not dealing with the data, you're dealing with an SSL connection that gets you the data. How do I get the key associated with that data? Well, I can't because I don't have a name. In CCN, you've got to have a name to get anything. The name is the fundamental to the communication. And you can always algorithmically go from a name to the key for the name. Right? You can just say, the key associated with this name is the name / key. Right? And if you want to go get the key, you present that name. And then you use the CCN mechanisms to retrieve it, because that's just another named data item. So you get absolutely trivial key distribution at an arbitrary granularity. It could be at the data item level, the single kilobyte level, it could be at the whole collection level, it can be at all your data level. You get to choose. But there's no technical barrier to making it as fine as you want it to be. So my program signed it with a signing key that I gave it. The way I gave it a key was I had a signing key that Park gave me when I was employed by them. So they gave it to me when I delegated. They delegated that part of the namespace. In fact, the delegation is giving me that key. So I use my key to sign the calendar program's key, and the calendar program uses its key to sign the data items. I'm not giving the calendar program my signing key, right? I'm delegating it the ability, I'm giving it a delegated key, a longer key. And the reason for that is you notice that the name of that key matches the leading name of the data item. And in our library dealing with collections, at the application level, we use that convention explicitly. We say, that's the realm in which this key is valid. So this key can be used to sign a calendar entry. It can't be used to sign a check. Right? It's a key, meaning is a very limited domain. If it's compromised, well, I'm sad, but the damage is limited. And that's coming for free. That's coming, again, because we've got these structured names. There are other things that can be checked from the same name. This goes across Park's network, doesn't have to, it could go across Bluetooth or other things, but if it goes across Park's network can check and say, if there's a data item that claims to be in the park.com namespace, it better be signed by a key that was authorized for the park.com namespace. So the network infrastructure is going to check that part of the signature and say, is the user of this namespace somebody that I want using this namespace, or is it somebody who wandered in off the street and is trying to inject data into us? And if the Park part of the key doesn't validate, the infrastructure says, nope, that's my namespace, you're not authorized to use it, I'm throwing this away. So that's the flip side of attack amplification. Right? Now, the attacker has to work against the entire network infrastructure. Right? You want to inject bogus stuff into Park, the first Park box that it hits says, you want to, my guys? No, sorry, your data's gone. Right? So rather than having a lens, we've turned it around and we can make all of the infrastructure defend us because the content's visible. What we're trying to accomplish is visible. And it's visible both at the data item level and at the certification level. The infrastructure can make the connections and use that to protect. So I'm going to use that as a segue to the security model. So I think I've said pretty much all of this. For TCP, because by design, the content's opaque. It can't help you in protecting it. All it can do is put an armor shell around it, but that can hurt you more than help you. We have this totally horrible trust model, again, because of our communication, armored pipe containers, talking to hosts. We try to do this root certified trust. That means you're outsourcing trust, and in my mind, that's the same as outsourcing breathing. It's a really bad idea, because trust is how we live. It's what makes our communities. But you don't get to do that at the network level. You have to trust who Microsoft trusts, or you trust who VeriSign trusts, whoever the root authorities are that can sign certificates. The intent was there would only be a few of those. They would be quasi-governmental agencies. They'd work with very high level of ethics, very high level of checking. Well, you look in the current Microsoft Internet Explorer, it lists 263 root authorities. They're from all over the world. Most of them I don't recognize. Most of them I wouldn't trust for a second, including up to particularly Microsoft. But my browser trusts them implicitly. Anything they certify, any of those authorities can certify the certificate that claims to be my bank, and my browser will believe it because a root authority asserted it was true. They didn't actually have to be the root authority who gave the certificate to my bank. Any of the root authorities are equivalent. So any of those 230 guys that gave a nickel to Microsoft, right, they're an absolute source of trust. And all your devices absolutely trust them. Anything they say, it believes. This is not a good world. It's just way too much attack surface, way too many high-value targets. If I want to protect my data at a fine granularity, so if something's compromised, I don't lose much, because I can't name content, I can't name keys. And so I get this completely unsolvable key distribution problem. When I try to set up security policies, like inside an organization, the way that people think about information security is in terms of what can be shared. Right? I have this set of information, I'm collaborating with you, I will share that set of information, but no other set. Right? We work on the information, it embodies our interaction. But you can't express that kind of policy at the network level because the network doesn't know about what, it knows about who. So what you have to express at the network level is who can talk to who. Your machine can talk to this machine via the firewall, and I'm careful to put on that machine the stuff that we can share. Right? So I try to manually make the what congruent with the who, and that doesn't work very well. Right? I can't put a separate machine for every project on the firewall, and if I mix a lot of it together, well, the sharing might not be what I think it is. The information can diffuse because there's not a hard boundary, and I can't check it because it's not visible to the network. The network just knows about things at the machine level. Okay, so the next few slides were largely dictated by Diana Smutters, our security guru, because she claims I'm totally incompetent to talk about security, which is completely true. So I'm going to be giving you her words with a little bit of annotation. So in CCN, we changed that. In CCN, every packet's authenticated, and it's not only authenticated, but it's publicly verifiable. Anything can verify any packet. Now, that's very different than current practice. The best current practice, it's fairly rare, but the best that you ever do in a TCP/IP network is what's called HMAC, a hashed message authenticity checker. And what that is you take a secret, like a shared random number that some set of participants know, you concatenate it with your data, then you can compute a one-way checksum of all your data plus the secret. Right? So this is a one-way checksum. You can't go from the checksum back to the data. So only the people that know the secret can authenticate the data. But anybody who knows the secret can authenticate the data. The problem is it's completely symmetric. Anybody who can verify can also forge. There's only one secret. And only the people that can verify can attest to whether or not there's any data integrity. No other party can, in particular the network can't. We do something different. We actually sign the packets. Signing, you do the original view, is you compute a one-way checksum of the packet plus its name. And then you encrypt that with your private key. And in the packet, you put a locator for your public key. So now anybody who gets that packet can take your public key, decrypt the checksum, and then separately compute the checksum from the data. If those match, they know that the data hasn't been modified, and the fact that your key, your public key decrypted the checksum proves that you were the one that signed it. Right? So you're getting not only message integrity, but you're getting the authenticity. Who signed this message? You're getting it from the public key crypto. Now, that computing a signature is expensive, for some measure of expensive, right? Somewhere between 100 microseconds and 3 milliseconds, depending on the algorithm that you're using on a current generation Pentium, 2 gigahertz Pentium. You don't have to compute a signature for every packet. There's lots of ways. Thing that was invented by Ralph Merkle called a Merkle tree, where you can use one signature for a whole collection of data, but you can put the incremental computations that go into that signature physically in the packet. Packet has to contain the log number of those. So if you've got 1,000 items, you need 10 partial computations in every packet. But you only do one signature computation. It's very cheap, so you can get very high level of amortization. There are similar things you can do with what are called ticket signing mechanisms. So you can make the signing operation be arbitrarily cheap. You can make the verification operation be relatively cheap. You can also make it probabilistic. It's the receiver that can choose what they choose to verify and when. They can choose to verify the first packet and trust the following ones. They can choose to verify every nth or some random number. They get to choose their amortization schedule. The big thing that you get from public verifiability is if you're allowing content to be replicated, if it can live at multiple places, you have what's called the Chinese telephone problem, that each of those copies can pick up errors, and the errors are persistent, because they live in the replicas, and then you make another replica and it has more errors. It has all the original errors plus new ones that came from the transcription. You need to be able to get rid of the replicas that contain errors. You don't want them to live in the network because they can impede your communication, they waste space. And attackers can inject data where they pretend it's signed, but it's not. Right? They don't know the keys that were necessary to sign it, but they can put all the metadata that looks like it's got a correct signature. And unless you actually do the check, you can't tell that the data is a forgery. You don't want to do that at every node in the network. You would like to do a system where the end nodes, the consumers of the data, check the data. And if they find that it doesn't check, they can go back to the infrastructure and say, that piece of data that you gave me was bogus. Now, the infrastructure, they don't know if you're telling the truth or lying. But if it's publicly verifiable, they can check and say, oh, you're right, it's bogus, and it looks like you're a trustworthy guy. If you tell me in the future, I won't bother to check. You can build up reputation systems and gossip systems that let you distribute the work of verification in the presence of replication so that you get valid replicas everywhere, doing the work at the edge, so you get scalability. As the edge grows, you get more places to do the checking, and you don't tend to concentrate the work in the center. Okay. Trust model, so you have to do security validation in some sort of trust model. And as I say, the one that we've got now, the God's anointed by the root authorities, they determine all trust. Right? That's a really bad one. Ron Rivest, who is one of the true gods of security, is the R in RSA and has invented just an incredible amount of fundamental security infrastructure. He got very frustrated by the state of certification in the 1990s. And he invented a very nice certification system called SUDSI, simple distributed security architecture. He published it in '96. He took it into the IETF, tried to get it standardized. It turns out that was a very frustrating experience. Some RFCs got written, but it didn't have the impact that it should have, in large part because it's a model that's really focused towards content, and IETF networking isn't content. But it's simple, it's extremely robust, it's completely distributed, the choices are completely local, you don't have to coordinate with anybody or anything, but it's been fully axiomatized. You can express it in formal logic, and you can validate that formal logic against standard security models, standard threat models. It means it's verified. That, I mean, you really can depend on it at a first principles level. And so in the slides, these are links. That's to Ron's Sudsy page. The axiomatization was done by Joe Halpern, and that's a link to his paper. It was done in '99. That's the trust model we use. I mean, it is very good, and nobody can match Revist for designing these kind of things. You use a lot of keys, signing keys for authenticity, and encryption keys for privacy. And you can make the keys be largely automatic, and that's a benefit of the names, because it's really easy to tie keys to data. It means that I make some new set of data, policy says it wants to be private. Part of making the new set of data, I generate a random number, that's the key. Right? Then I encrypt that key under my public key or under group keys, spread it throughout the world so they're replicas and it can't get lost. Now that data is private. And it's made private, right? It never lives in the clear. In normal networking, that would give you an unsolvable key distribution problem, but CCN is perfect for key distribution because you can name keys, and anything you name you can distribute. And they're replicated so that you get very high reliability. The way the Sudsy trust model works is when you have these keys, particularly signing keys, the reasons that I use for trusting a key don't have to be the reasons that you use for trusting a key. So I get a key from my bank, and I decide that I'm going to trust that because when I set up the business relationship, we exchanged keys. And the key and the message from them, I can prove to myself it was derived from the key that was established when we did our business relationship. And that's the way I want to do business with my bank, right? I want to have a very high level of trust in the communication, and if I get a key that I can't trace back to the business relationship, then I don't believe it's my bank. That's my choice. You get a credit card offer from my bank. You look at it and say, well, did this really come from this bank, or is it from some scammer? You can check the key in a registry of keys. You can check with your friends to find out if they've seen that key before. The way that you establish trust in that key has to do with your context for the information, how you value the information, as opposed to today where there's a one-size-fits-all. We check with VeriSign and see if they sign the key. There's a fundamental change that happens at the network management and the network configuration level when you put in security at the bottom. And now these are my words, not Diana. So John Maynard Smith, the evolutionary biologist who gave us evolutionary game theory and a lot of mathematical insight on how ecosystems and organisms create themselves, how they self-organize and structure. In one of his books, he said that identity creates organism, that the thing that's fundamental to making an organic unit, a cooperative unit, is a shared notion of identity. And you get it in things like bodies because our identity comes from our DNA. But we get it in other things like communities and families because of shared context and shared experience. You can't make networks today that behave organically, that have levels of cooperation in the network because there's no notion of identity that you could use to bootstrap that organism, that cooperation. If you move to a content view, several things get easier. One is your configuration is dead simple. The only thing that you ever need to configure is the signing key. It includes the identity, and it's a structured key, so it includes your identity at many levels, right? Your individual identity, but your role, you know, I do calendars, your organization, I do calendars for Van and Park. Right? There's many pieces of information that are embedded in that identity that you can use to say who you should trust and at what level. But another interesting thing is in host-to-host communication, point-to-point communication, there's always two ends. And so you have to configure the two ends to agree. You have to configure the same information in 2 points. If you have to configure the same thing 2 places for stuff to work, there's a much better even chance that it's not going to work, right? Because there's lots of ways to misconfigure. If you don't have point-to-point communication, if you're talking about stuff, not to stuff, all configuration is single point. You never have to get agreement. You're saying what you want. You know what you want. Nobody has to agree on that for you to say it. They have to have it in order to respond, but they don't have to agree. Right? So you get this really robust configuration, single point configuration that you can't misconfigure because it doesn't have any agreement involved in it. And the configuration includes some notion of community and identity. And you can use that as a sense of self. So as you're learning about the world, you're learning about the things around you and what you should do in that world, when the outside world tells you things, gives you information, tells you about its context, you know what you can believe and what you can't believe. You know what's relevant to you because you can filter it through your identity. And they have to put their identity in everything that they're telling you. So you can say, I'm a router and you're giving me adjacencies and we're the same organization, we're the same network, I guess I'll believe your adjacencies. If you're not the same organization, you're not the same network, you've got a different signing key, well, I'm glad to know about your adjacencies, but they have nothing to do with me. So you get an easy way of getting trust without additional configuration. And the example that I gave about defending a namespace, all of the infrastructure can recognize not self in addition to recognizing self. Right? The two concepts are complementary. So you know what's not you. You know what you should defend against. And you can muster all of the infrastructure to protect things that need protecting, rather than having to localize those. And we can't do that with current networks. And we can't do it because our security is an afterthought. And this is a deep annoyance of mine, that we've always made security an afterthought, but it's not. It's fundamental, and it's fundamental to organisms, right? Security is what gives us identity. We tend to think of security in terms of privacy, in terms of encryption. But if you look at Riva's webpage, a lot of their work has been on signing, it's been on identity, because identity is a much more fundamental operation and a much more important operation. It's really a Swiss Army knife of security. And the privacy, I mean, that's interesting, being able to encrypt stuff and keep it private. That's good, but it's not nearly as fundamental. I mean, what's really fundamental is identity. And identity doesn't have to disturb privacy. In fact, it's the other way around. When most of Ron's recent research has been on micropayment systems and small transaction systems where the users want anonymity. And you use signing to create the anonymity. What you do is you sign the money so that you don't have to identify the principals. Right? And you can sign the money in a way that it's not traceable. It's identified as money. It can only be used once. But you can't tell who used it. You can't tell what it was used for. And that's, again, it's a first principles assertion. It's a very hard guarantee of privacy. It's a mathematical guarantee that nobody, no matter what information they have available to them, I mean, it doesn't matter if you're Dick Cheney. You can't tell who used this money to buy what. Right? There is no information that would let you reverse the spending operations and track it back. And that's from a signing operation. Right? And it really is a Swiss Army knife. And it's something that we should be integrating into our thoughts very early, and we don't. At least the tendency in the US is, I don't do security, I don't know security. All that security stuff is magic, right? And that's a poor point of view that really impoverishes our world. With that flame, I'm going to go on to the node model. I want to talk about, so we've talked about the way that CCN views content, and it's a different view of content, right? It's the content itself, not its containers. And now I want to tie that to the moving parts, how the nodes work. For that, I've got to talk about what are the packets that it deals with. So we've got two kinds. There's an interest packet, which contains a name, and a little bit of other goop that I'll get into later, and a data packet, which is what you respond to an interest with. So an interest is asking a question. It's sort of like an HTTP GET. It's saying, does anybody have any data in this collection that matches this name? The data is an answer. And the data, because you have to secure the binding, includes the full name, the actual data, and the signature information, and then some other goop that I'll get into. And we encode this whole thing in binary in something that can be one-for-one transcoded to XML so that you can lump together multiple units of data, and you can extend any of those fields if you need to. In particular, you can add an arbitrary amount of security annotation. Now, I've been giving you names like that, like they were human-readable names. Those aren't CCN names, right? That's something that you're comfortable seeing, but a name in CCN is this opaque object, and the only thing that CCN cares is that it's a hierarchically structured object. Right? It uses the structure, but there's nothing else that it knows about. This is how a name's represented. It's a count of the number of components. It can be one if you want to use self-certifying flat names. I don't think you should, but you can. One component, that's fine. And then for each component, there's a count of the number of bytes in the component and that many bytes. So arbitrary binary data, we don't care. The only assumption is that there's hierarchy, and I'll tell you why in a second. If you want to encrypt your names so people can't see them, that's fine. If you want to put arbitrary binary data like the packet signature, the SHA-256, that's a real SHA-256. It's not an ASCII encoded version. Right? It's already taking a lot of bytes, and we don't want it to take any more. Why hierarchy? Well, it's just same reasons as IP. You want to do longest match lookups because they let you aggregate state. It means that as you get far away from places where the content might live, you don't have to know the details. You just have to know the place where there are more details. You get that by doing what in IP is called the longest match lookup. You find the longest prefix that matches the address that you've got. What we found with IP is that gives you log-n state scaling in the core. As the network grows, the state grows only as the logarithm. So even though we've got 3 billion hosts on the internet, we've got on the order of 300K roots in the core. And that's a completely tractable set of state, even for a global network. Now, this only applies to globally routable names, of course, just like some IP addresses are not globally routable. Net 10 addresses, 192.168, right? They don't even appear on the routing tables. And CCN has an equivalent of local names. Now, we're using longer names, right? They're often derived from human-readable names, and they've got maybe content identifiers on the end of them. And their variable length, first thought is, wow, it's going to cost a lot more to do the packet forwarding because packet lookups are going to be more expensive. Well, if you looked, and the theoretical computer science conferences over the last decade, the progress in hashing has just been absolutely astounding. It really boggles the mind. There was a paper in the last talk from Martin Disfelbinger of University of Ilmenau and several colleagues, where he's computing collision-free hashes in linear time on 1 billion elements with the cost of about 6 microseconds per element, right? And 99% load factors in the hash table, right? So it's a hash table with 1 billion elements, collision-free, single probe will always get the right element, and all the space is used, no inefficiency. You know, when I was growing up, that was impossible. You couldn't do that. Don Knuth said that you couldn't do that, right? You couldn't load it more than 30% and you would have collisions. But between Rasmus Page at University of Copenhagen and Martin, light years progress has been made in hashing. None of that can be used by IP, unfortunately. And that's because the structure of an IP address isn't explicit in the address. The way that you find out what is the net part and what is the host part of an IP address is by looking it up, because that information is kept in the routing table. And that means you can't hash the address to look it up. Or if you want to hash it, you hash it a bit at a time. So in an IPv4 address, you do 32 lookups, one for each prefix of the address. You can hash those, but that's a lot of lookups. Right? But you can't hash the address itself because you don't know what's the prefix. And the only way you can find out the prefix is by looking it up, which means that IP lookup structures, particularly for IP6, where you don't have the option of doing it a bit at a time, the lookup structures all tend to be either radix tree structures where you have to do a tree walk, and when you hit a terminal node of that tree, you found the longest match. So there, the routing table is telling you the address structure by terminating the walk, or that you can do in software, and you can do it fairly fast. It's log n cost, but you know, it's still a tree walk, a lot of memory accesses. The other option is if you're doing it in hardware, you put in a TCAM, a ternary cam, which can do the match in parallel, but at a fabulous transistor budget. So DRAM is 1 transistor per cell. You make big memories out of it, gigabyte memories out of it. SRAM is 12 to 14 transistors per cell. It's really fast, so you can make the memories that sit right on the end of your serial to parallel converter for very high-speed links. But you pay an order of magnitude density cost. So for the same amount of dollars, you get a much smaller SRAM. TCAMs are 100 transistors per cell, right? Because you have to put the matching logic and priority logic in every cell. So it's 2 orders of magnitude more expensive, or 2 orders of magnitude less in density. You can't put very big routing tables in TCAM, or you spend a lot for the routers that use it, right? And this is a property of the way IP lookups work, the fact that the structure is implicit, not explicit. So badly wanted to fix that for CCN. CCN structure is explicit, which means that you can use hashing and all of this wonderful work over the last decade for lookups. And so even though the names are longer, you can look them up as fast as you can look up IP names, because the explicit structure enables a lot of recent research. Meaning. So we've got these names, what do they mean? Particularly the prefixes. Well, one of the big successes in IP was the routers don't, the names don't contain their meaning. The router has a set of rules for dealing with names. It does a longest match lookup to find them in a FIB, in a forwarding information base. But the meaning of the name, where it goes, that's completely determined by the contents of the FIB. And that's let us evolve a lot of different meanings. So it let us evolve this host addresses, the 127.1 address, right? That didn't require any change to the IP40 model. What it Cause is the way that you set up a fib is you never send 127.1 to anybody else. It's always you. And if you don't accept it locally, you drop it on the floor. And if you hear it from the outside world, you drop it on the floor. Local use addresses, net 10, 192.168. They're addresses that are deliberately not routable. If you try to push them across a boundary, the other side of that boundary refuses to accept them. They have different meaning in different networks, so you're free to give them local meaning. Some addresses have global meaning, net 18, net 13. They mean the same thing all over the world. That's defined by the way that you set up the routing table. So the semantics of addresses come from policy considerations in how you set up FIPS, how you can do the forwarding. It's the same for CCN. The node machinery doesn't give any meaning to addresses. In particular, addresses can have local meaning, which gets reused. And the one that I would really like to see in place, so that we didn't do this cable dance that we had to do this morning, was I have this presentation, which has a globally routable name. You could pick it up from anywhere in the world. In this room, there's a projector, and I can talk to that projector on a local name that's the same in every room. If a room has a projector, I can say this room / projector, and I'm talking to the projector. Right? So I can wire that into a piece of software that I never change. And when I want to do a presentation, I go to the projector and say, projector, here's a presentation. Put it up for me, please. Right? No wires to hook up. It's a name that rehooks itself up. It's a contextual name. And I can do lots of variations on that theme. It can be this room, it could be this meeting, it could be my family. Names that have useful local meaning that changes based on the context. And you want to make the name static and take advantage of the fact that it's being rebound. And particularly when you're doing more coupled worlds, you're doing energy management. So I would like to talk to this room's thermostat or this room's lights. If I want to do that with IP, what's the IP address of the light switch? Right? Who knows? How could I find out? There's just no way to express that. But in a content model, it's easy to give it a name. And if there's a communication infrastructure, it's easy to talk to that name. And particularly for lights, we're in the middle of a huge revolution in lighting. We're going from these very slow fluorescent and incandescent lights to LEDs. LEDs have the property that you can modulate them. You modulate them very fast, gigabits per second. If you're using them for lighting, you actually would like to modulate them, because the way the human visual system works is if the light's turning on and off faster than what's called a flicker fusion frequency, we perceive it at its brightest intensity. We don't see it turning on and off, and we don't see the average intensity, we see the brightest. That's just because the phosphors in our eye are fairly slow. So you save a lot of energy by modulating an LED light. Rather than just modulating it with a sine wave or some random frequency, why not put data on it? Why not have the room announcing what's in it? Why not have the photodiodes that we've got, the cameras in our laptop and the ambient light sensors in our phones? They could be reading the lights, finding out what's going on at the university. We're deploying all sorts of new local data-capable infrastructure. It's ideal for distributing content, could give us a lot more awareness of the environment and could give us closed-loop coupling of the environment. It's not very amenable to an IP model, but it is very amenable to a content model. More rambling. Basic operation of CCN, so we talked about this before. If you want data, you broadcast, logically broadcast. You can do it over a point-to-point link, an IP tunnel, anything you want, but the basic mechanism is a dissemination, a broadcast model. You say what you're interested in, give the prefix of the data that you want. It's a collection of data, the stuff that matches that prefix, and anything that hears the interest can respond. If it has a data item, it can respond. So that's not the way Google works, that's the way that IP works. IP, you can't be interested in very much but packets that have your name in their destination address. But that's how IP works. When you put a node on a network, it does a broadcast called an ARP that says, This destination address, anybody interested in sending packets to this destination, send them to this MAC address. So it binds the logical identifier, your IP destination, to a physical identifier, some interface MAC. Routing can propagate that. They don't have to propagate the host part of the address, the entire address, because it can be covered by their prefix. So they need to know that binding to talk to on the local net, but they don't need to tell the rest of the world about it. And essentially you're getting interest in the CCN nature of interest. We call them routes, but they flow out through the world, and packets follow those. That's a trail of breadcrumbs that cause your packets to be delivered. Here's a picture of that. So some host over here, 1, 2, 3, 4, it ARPs, it broadcasts, says, I'm at that IP address. It's got a couple of routers on the boundary. They look at the ARP, remember where that host is. They remember its MAC address so they can talk to it. But they're in charge of subnet 123, so they don't need to advertise the 1234 because the 123 identifies anything whose address starts with 123. So the 4 is redundant, it's irrelevant. So they just are propagating their prefix. Subnets get to the border. This network is telling its network identity, 1.2, right? So it doesn't have to propagate subnet level detail. So what we end up with is the 1.2 getting distributed via the whole internet. And now when anybody wants to send to that host, they send a 1.2, gets to the border router. It can look at the destination address and says, oh, it needs to go to subnet 123, so it sends to that subnet, and then the border routers know what the host is. Right? So we get fine-grained information close to the host, very coarse-grained information far away. That's what gave us the nice scaling. That's just how CCN works, no different. Transport level. So here's something fairly exotic. You sent out this interest. There's some matching data. The matching data coming back, it makes the interest go away. So the data follows the interest. You can view as the interest is flowing out, it's laying down breadcrumbs. That's just like IP routes. But we have the model that as data is coming back, it consumes the route. It eats the breadcrumb so that other data items can't follow it. You need to express a new interest in order to get additional data items. If you want a lot of data in progress, if you've got a big bandwidth delay product that you need to fill, you can express several interests in parallel for different data, and you'll get all of that data simultaneously. And that's similar to a TCP window. In fact, this whole mechanism is really similar to a TCP window. If you look at how a TCP conversation is working, the sender sends until it fills the window. The window tells it how much it can inject into the network, and then it stops. And it's got to wait for an ACK before it can send new data. Generally, you get an ACK in for a packet, and the sender that allows the sender to send a new packet. It exposes another chunk of space. And so you have a sender that's turning ACKs into data packets, and it basically consumes the ACK. And symmetric thing is happening on the receiver. It turns data packets into ACKs. That essentially consumes the data packet. They're working in a pairing, in a flow balance. If you've got this pairing, if you've got this balance, then there's a beautiful piece of work by Frank Kelly of Cambridge, a book he published in '79, which I didn't read it until '89, and would have saved me a hell of a lot of time if I'd gotten to it a decade earlier, called Reversibility and Stochastic Networks, where he talks about the properties of this detail balance. And the first principles properties are, if you construct a network that's got flow balance, or even approximate flow balance, some affine transform of a balance, then it's absolutely robust. It's Lyapunov stable under arbitrary traffic and arbitrary load, which is basically, it's why we could grow the internet. It doesn't matter how big you make it, doesn't matter how many hosts you put on it. The balance property lets all of the interested parties control the traffic so that it can not get very far out of balance. So there's a bound on how bad it can get. Now, that bound can still be pretty bad. It's the amount of buffering that we've got in the network, and we tend to put a lot of buffering in the network. And so things can suck pretty badly while you're waiting for all those packets to go through. But it's a bound, and it's a hard bound, hard mathematical bound. that says you can grow this network. So it's a really important property, and this is another one of those things that should be taught, isn't taught. If you're designing protocols, you want to think really hard about the flow balance and the symmetry properties it implies. TCP's used it to great effect. CCN's using it for the same reasons. And TCP uses it in a unicast scenario because it's point-to-point conversation. But the nice thing about reading Frank's work is it works at the traffic level. It's, can you pair a packet with another packet? We pair interests and data. And they're broadcast. Both of them could be broadcast. Full multicast scenarios, replication scenarios. It's still stable. We struggled for decades trying to make multicast versions of TCP and failed. It's really hard to make multicast transport protocols. And part of that is not understanding the underlying dynamics and the balances that you have to maintain. Well, you can show that balance for CCN formally. We haven't done the work to show it in simulation. We've done it at small scale in our prototype implementation, but it maintains it. You know, it works. What Frank said works. So I said I was going to talk about the machinery. Here's the machinery. Start with the IP machinery. So this is just straight out of 791, right? You read the RFC. This is the picture it gives you. You've got interfaces that are point-to-point wires. You've got some network core. It's got a table in it called the FIB, which is the forwarding information base. It tells it for a given destination address where you should send the packet. And these interfaces, because you're stat muxing, the interfaces have to have a buffer in front of them. That's right, because there is no global scheduling system that prevents packet conflicts. It's perfectly reasonable to have a packet arrive on interface 0 and 1 simultaneously bound for interface 2. Right? So even if all the wires are the same speed, you're going to instantaneously overload the output interface by a factor of 2. And there's no requirement that those interfaces be the same speed. Very often, if some are local interfaces and some are long haul, the locals tend to be many orders of magnitude fatter, higher bandwidth than the long haul interface because of the economics of bandwidth. So you're required by the design of the protocol to have a buffer to handle the transient overloads and the rate adaptation. And the packet forwarding model is, packet comes off the wire. First thing you have to check is its destination address me? Is it bound for this node? If so, you punt it up to your transport stack. If not, you've got to prevent loops in IP because it's not aware of the data is opaque. So every packet has a time to live, which is basically a loop killer. You decrement it at every hop. So you check the time to live. If it's not you, you're going to forward it, but you're not going to forward it if it's off its time to live. Check it. If it's non-zero, you decrement it and you can forward it. The way that you forward it is look up its destination address in the FIB, do a longest match lookup. The FIB contains an outgoing interface and you put it on the queue for that interface. And that's the packet processing. And that FIB can be exactly one outgoing interface. In IP, you have to forward on a tree, this gravity property. You have to do loop-free forwarding because if you had loops, it would kill the network. And that means, in the way that we normally architect is, no matter how rich the network graph is, we overlay a spanning tree on it and we forward via that spanning tree. And the tree has the property that there's one path between any two nodes. It means there's only ever one outgoing interface in the FIB. Here's the CCN node model. It's got more stuff in it. So our interfaces are broadcast. They're not wires. Abstractly, they're radios, right? You can broadcast an interest on them. They can be point-to-point links. They can be tunnels over IP to any point in the world. We don't care. And they can be applications. CCN, there's no difference between demuxing to a local app and demuxing to some foreign agent. It's demuxing. And so there isn't an is it me decision, right? That's just demuxing to a local app. And you need that if you're doing multi-point protocols because you may have a service agent locally but the data may be available multiple places, and so you want to ask the local copy, but you want to ask others. So whenever you've got a protocol where you can fan data out or fan data in, then if you do the classical layer 3, layer 4 split, you end up hosing yourself because you have to either send the data up or out. And if you want to send it both ways, you can't do it. That's not how your protocol stack is organized. So when you do many-to-many broadcast communication, you need to put applications in the same framework that you put everything else in. And that simplifies stuff. 3 different data structures. One we call the content store. That's where you remember data that you've seen before. And you view it as the buffer memory. In fact, it is the buffer memory in a normal router. Same memory, it's got a different replacement property. You do LRU rather than MRU replacement. You don't treat it as a FIFO. But it remembers the packets that you've got. You can verify all of those packets, so you can get rid of corrupt ones. And there's an index structure that lets you go from the name into that content store. So I said that when you send an interest, it lays down breadcrumbs, and then data follows those breadcrumbs back, and it consumes them in the process. Well, that's embodied in this pending interest table. So that's an interest that you couldn't satisfy and you sent on to somebody else, but you have to remember it, so if they give you data, you can give that data to the people who originally asked you. Right? So it's got the name from the interest and the face that the interest arrived on, and so when data arrives, that's the face the data is going to go out. So that's the breadcrumb. And for every interest that you can't satisfy locally, but you forward remotely, there's going to be an entry there. Then lastly, there's a fib. It looks just like an IP fib, but rather than having a single outgoing interface, it's got a list. And that's because in CCN, data can live multiple places. And so what you put in your fib is all the places where the data might be. In IP, it's a different semantic. The interface, output interface is where the data must be. When you announce a prefix, the contract that your routing protocol is making with the network is everything covered by that prefix is reachable via me. And that has to be the contract, because the people that you're telling the prefix can only send the data one place. Right? And so if they send you a datagram with an address in it, you damn well better be able to handle that datagram. Right? You have to get it closer to the destination, because they only had one choice and you were the choice. Right? So you get global dependencies in IP routing because you have to put on a spanning tree, where you have to be able to handle all the traffic covered by a prefix. There's no such global dependency in content routing. Right? If there are 3 places that the content might be, then CCN is perfectly capable of asking all 3. It can ask all 3 simultaneously, and 2 may not have it. Only one needs to answer. So you don't have global dependencies, you just get local dependencies. You get a much weaker contract. You have these 3 tables, you still only do one lookup. An interest comes in, you have a single index structure, you look up the interest, and I got a picture, doesn't show very much, but I'll at least put it in. An interest arrive. We're looking at a state where something on that wireless network is trying to pull down a video, right, which has got that name, Partacom videos, widget.a.mpeg. And it's version 3 of the video. And you can see up here, we got block 0, the first block of the video, and it's in the content store. And block 1 has been requested, it's in the pit, but no data has come back yet, so it's still pending. And the thing that's asking for the video is asking for the next block, so it's asking for block 2, the 3rd block of the video. That interests arrive. We take the name there, we look it up in our index structure, longest match lookup. It doesn't match anything in the content store because there's no S2, and it doesn't match anything in the pit. Again, there's no S2, there's an S1. Longest match lookup, it does match the park.com and the fib. So we don't have the data the application's interested in, but the fib says we might know where to get it. And so we'll forward the interest. The way that we forward the interest is we take the face list out of the fib. The question arrived on face 0, and you never send a question back out the face that it came in on. You know, that's flooding semantics. That would be stupid. It's just going to loop. So if you're going to forward it, you remove the face that it arrived on, which is 0, and you send it out face 1, presumably to some server at Park. So that's going to bubble it upstream. And you make an entry in the PIT that said, I'm asking for park.com widgets mpeg/s2, right? So it says that I've got a second pending interest, one that's being propagated. Packet came in, it's a single lookup, right? It can be 3 different places, but they have a priority order. If you've already got matching content, you always want to return it. So if you get a content store match, you satisfy the interest, you send that data out the wire, and you're done. Throw away the interest. If you get a PIT match, then either this is a new interest in the same data, so somebody on a different face is asking for data that you're already trying to get. If that's happening, then you simply add that new face to the PIT entry and say, okay, I'm getting it, and when it comes in, you'll get a copy as well as the guy who asked the first time. Right? So that requesting faces, that's another list. Right? And if you get a new PIT entry for data you've already requested, you add it to that list, and now you throw away the request because you've remembered what you need to remember. If it's a duplicate, or if it's coming in on the same face, it's a guy that's impatient and he's asking you again, or somebody who didn't hear the first request and is asking again. And when the data comes in, you're going to satisfy their interest, so you throw away the interest. You don't need to do anything. Right? So there's a priority. Look it up in the content store. If it's not there, look it up in the PIT. If it's not there, look it up in the fib. One lookup where you order the entries in the lookup so that you get the entries in priority order. Right? And that's easy to do with a particular kind of hash table called a creep, and a treep, a priority tree. And there's probably other structures that do it as fast, but it's hash, it's an order 1 lookup. So 1 lookup, same cost as IP, more data structures. When data packet arrives, so we sent the interest out that interface, data packet comes back in. We look up data packets only in the PIT. Well, that's not strictly true. Look up the data packet. If it's in the content store, it's a duplicate and you throw it away. Right? And the data is idempotent. Right? Looking up a data packet means up to and including the data itself. Right? So if you find it in the content store, you've got it unambiguously. Right? Up to the SHA-256 checksum, you've really got this data packet. And so you don't need the duplicate copy because you know it's a duplicate. And you toss it. What that means is content can't loop in CCN. Right? If data goes around a loop for any reason, as soon as it gets to a place where it's already been, you look it up in the content store, you say, I've got that, and you throw the copy away. Right? So you suppress duplicates at the content level because it's a content protocol. That means that you can use this simple diffusion flooding paradigm because the data is recorded. So we look up the packet. If we find it in the content store, it's a duplicate, we discard it. If we find it in the PIT, it's something that we asked for. What was this one? This was S1, so I do find that in the PIT. So somebody asked for this. What that means is I record the packet in my content store. I got something that was asked for, it's relevant data. And then for each interface that's listed in the PIT, I send the packet out that interface. So what that is, I add something to the work list of the outgoing interface that says, ship this packet that's now in the content store. And I say it that way because in CCN there aren't queues. Conceptually, the model is a router, an upstream node, always satisfies requests from its content store. What you're asking for is something that's in the upstream's content store. If it doesn't have something in its content store, but it knows a way to get it, then recursively it will ask its upstream for that stuff, put it in the content store, and then send it to you. But you're always satisfying requests out of a memory. The memory in CCN is explicit rather than being an implicit buffer memory in IP. And because of that, you don't need queues on any of the interfaces because you don't have to do rate matching. They get the data when they want to get the data out of a random access memory, and they get it in the order that they want to get it. So the service policy is not the sequential policy that's motivated by queues, but it's an instantaneous policy per face that says, okay, what data do I need to send now based on the downstream demands on me in the downstream contract? So you don't have the ordering implications. You don't, roughly 50% of the QoS problems that we see on the internet are artifacts of queues. The fact that a queue introduces this big delay and it's serial. You can put stuff on the end of a queue. You can't put it on the middle. You can't service out of the middle. If you get rid of queues, then you get rid of that 50%, because the service policy can use the fact that you're servicing out of a RAM. And it can be much more responsive to the downstream demands and to the instantaneous changes in those demands. So we've gone through the node behavior. Let's do a side-by-side. So what I've just been saying, these are the same parts that are in an IP router. They're just combined in slightly different ways. The buffer memory turns into the content store. Same memory, same amount of memory. All you're doing is changing the replacement policy. Goodness is not in a queue, in a FIFO buffer. You want to keep it empty all the time because it's a shock absorber. And if it's not empty, it can't do its job. So you forget what's in the queue as quickly as you can. And that's good for the TCP protocols because once you've sent that data, it's of no further value to you. But given the relative costs of bandwidth and memory, actually the stuff in that memory is really valuable and you don't want to spend bandwidth to refill it. So the model in CCN is, no, if you've got it, remember it and use it again so you don't have to spend more bandwidth to get another copy. If you've already got a copy, great. So once data's arrived, you hang on to it for as long as possible. So that's a different replacement property on the memory. It's still memory, but you're going to an LRU replacement rather than try to forget as soon as possible. But it is the packet buffers, right? You post a buffer to a face, the face fills it with the bits that arrive. Then you look up its name in this index structure, and if you want to remember it, right, it's a data packet that arrived that satisfies from some interest. What you put, the way that you put it in the content memory is you put a pointer to that packet, the one where the bits landed, right? They came off the wire, they landed in some chunk of memory. You put a pointer to that memory in the index structure. You don't copy anything. This content memory isn't like some database, right? It's where your packets live. And so you're not moving stuff around, you're just remembering them in this index. The really new thing in CCN, that's not in an IP router, is an index structure, and that's so that you can reuse stuff. What's next? Fibs, basically identical, except CCN doesn't need to forward on trees. So you can have lists of interfaces rather than a single interface. Transport, because you're doing multi-point, a lot of the transport state turns into the PIT. And it's because the data could need to be replicated. So the same reason that when Cisco did PGM, their multicast transport, they had to stick part of it into the routers is because the data needed to be replicated. It's the same problem. You need to be aware of the local connectivity in order to duplicate data. And so a lot of the layer 4 stuff, it doesn't make sense. It has to move down. There isn't a me test for the same reason. If you're doing multi-point, me just has to be completely symmetric, the same as any other interface. And so you forward to apps the way you forward to anything else. You never modify data. There's no TTL check. Nothing can loop. So there'd be no reason to do it, and we don't want to modify packets because it means that we can't assess their integrity. But that means that if you're doing particularly a silicon pipeline, you can do it a lot faster, because a lot of an IP forwarding ASIC, a lot of its real estate is involved in the implications of the TTL update. You have to rewrite the packet. So that really changes the flow-through semantics, and it's not just the TTL, because when you change it, you have to also change the checksum. So there's some computation and several fields that have to be updated. None of that happens in CCN. Right, so you don't have protocols like ARP or ESIS. IP requires that you have layer 2 point-to-point identities because it needs point-to-point identities. You know, that's what it speaks, that's what an IP address means. And so it has binding operations to set those up. You don't get them in CCN. So those are two simplifications. There's a complication. You have to handle multi-access interfaces, broadcast interfaces. And the canonical problem on a multi-access interface is a success disaster. You ask for some piece of data, and 100 guys have that piece of data, and they all try and give it to you. And they were synchronized by your question, so they all try to give it to you at the same time. It's called an ACK implosion. The MAC level protocol will resolve the contention so that they don't put their bits on at exactly the same time, but it's a huge traffic burst. And it's also doing nasty things to the MAC. It's driving it into a deep congestion state. So you don't want that to happen. Long ago, when we were doing multicast protocols, it became clear how to do protocols to avoid that. It's called a suppression mechanism. So you're broadcasting the question. You want to do the transport equivalent of CSMA, which is you want to randomize the responses over time and have the responders broadcast so all of the potential responders can hear the first responder, and they then turn off and they say, okay, I don't need to respond because somebody else already did. So rather than having everybody respond instantaneously, you want to spread them out. You may have to spread them, if there's potentially a lot, you could spread them out over a long period of time because of the birthday problem. It says that if you really want to make sure that only one responds, then the time interval has to go like the square of the number of potential responders. So if you've got 10 guys, you've got to wait for 100 time units in order to not have them conflict, not have two in the same response interval. That's pretty grim. To get around the birthday problem, what you try and do is partition the responders. So you make some rule for who should respond first, so that within the partition, the numbers are small, and so you don't have the n squared doesn't bite you. In a partition, if you got one guy, it's a big win, because 1 squared is 1. So there's a simple prioritization rule for CCN. If you created the content, you're very high priority to respond. You're the guy who made it, right? You should get to answer questions about it. If you didn't create it, but you learned it off of some other wire, hypothesis is it wasn't created on this net, and if it was, the guy who created it will respond. If you learned it from some other wire, then your second priority to respond. And so you're a router, you got the data via some other source, or you learned it in another environment and you brought it here. So you can source it onto the net. Then the lowest priority is if you learned it on this wire, your lowest priority to respond because many other people learned it on the same wire. And so you should randomize over a big interval. With that priority rule, you can do a simple suppression where if the content is being created on the net or being sourced on the net, there's no delay at all, right? The creator just immediately sends you the data. If it's being gatewayed from some other net, the gateway responds after a very small delay with the content. It's just making sure that the creator's not there. If it was learned on this net, but the original creator of the gateway went away, then anybody who's got a copy will give it to you, but after a substantially longer delay. But you only do that for the first time. We've got this name structure, and it can remember stuff about this name prefix. So you remember in the prefix, if you responded last time, if you were the one that won the suppression game. And if you won last time, then you get to send immediately next time. And you get to do that for n many trials. So you amortize the cost of doing the suppression by essentially doing an election once via a contention mechanism. And then after that, you use that election for some period of time, until you run out of data or it's time to run a new election. And at that point, you run a new election. You can therefore deal with this broadcast interface as if it were a point-to-point interface. You don't have to deal with contention issues because you've got some memory. Now I want to say some heretical things about QoS. If you look at where there are quality of problems in the current internet, they're not distributed throughout the internet. I'm having a phone call, Skype call, and I'm losing big. It's not because I'm losing a little bit at 1,000 points along the internet. I'm losing at one point in general, right? There's some exchange point, peering point, choke point, the return path, the tail coming out to me, the tail going to the other participant. There's some fast to slow transition where a lot of traffic is piling up and stuff is getting lost. Because the only place you get queues are where you get a fast to slow transition. And there aren't many of those. That doesn't do you any good. I mean, you can know that, but it doesn't help you fix the problem. The call still sucks. And it's because the communication model in IP is this sort of action at a distance model. We want the abstraction that you have a single wire between the source and the destination. And congestion is a property of that virtual wire. And its components, its individual elements, they're not visible to the endpoints. There's nothing you can say about it. I mean, there's tools that you could run, path care, trace route, things that will tell you what's going on there, but they still don't help you. You might be able to identify the problem, but you're not going to be able to get anybody to fix it. So for IP, the observation that congestion tends to be localized, is properties of the engineering of the infrastructure, that doesn't help you. That localized congestion is generally half the problem. There's another half the problem that comes from IP's unidirectional model. And my example of this congestion is my son's just completely addicted to computer games, right? He never sleeps. He grabs food from the kitchen, goes up to his room, and he's just continuously immersed in these games. And they send huge volumes of data over our internet link, which, because I live in the US, is a slow link. My wife and I are trying to get work done over that link, and we have to compete with his goddamn gaming traffic. And we can't tell our ISP that our work traffic is more important than his gaming traffic, right? It's because the queues are in the direction of the ISP to us, right? But the interest, the value of the data in those queues is in the us to ISP direction. And there isn't a channel that goes from us to the ISP. There's channels that go from us to the ultimate destination and back again. But there isn't a local communication channel where I could say, I'm the guy that pays the bill, send those bits first, or send his bits last, right? It's not a way to express that. So I tried to make the point earlier that in CCN, all communication is local, and it's in the CCN model, the communication is local. You're talking to an upstream, and it's a bi-directional communication. You send an interest, it sends a data. Right? Some of the annotation that goes in the interest says, This data is more important to me than anything else I've asked you for. Right? When you get data that matches this interest, and you have a choice of 10 things to send this first. Right? So there's an explicitly, because the upstream agent is in the protocol. It's the thing that you're sending your interest to. Right? You also communicate your utilities to it. And because there's this flow-balanced interest data communication, it can react to that loop. It can say, okay, I'm pulling the stuff out of the content store, and I don't care about the order, but my customer told me he cares about the order, so that's the way that I'm going to pull it out. So the local communication gives you a channel to remediate this problem, the lack of the detailed control over the bottleneck link, because both ends are explicitly modeled. It's not action at a distance, it's local action. And each of the links is treated differently, right? So I have a business agreement with my ISP. They have a different business agreement with their ISP. And over that link, they have their own utilities. Their utilities can be, I sold my customer's telephony service and deliver on that telephony service all the telephony traffic, which I rate limit and admission control. I want you to service that first. That's their agreement. They don't have to have the same agreement that I have, because it's a different conversation. And so because it's local and because it's pairwise, it can reflect those local agreements. It's not a one-size-fits-all, and it's not an action at a distance. And the part of the problems that have to do with queues, there are no queues. So you can just punt those. But this last line is saying what I just said about ISP agreements. Whenever you're aggregating, aggregates can create problems. And so you have to deal with how you want to service the aggregate. And you do that in the context of a business agreement. Either customer-provider business agreement or provider-to-provider business agreement. And if you model the individual links, that's easy to do. Boy, I'm going real slow. I want to talk about routing. Routing's recently become an area of active research, and there's just very exciting things that are happening there. Very scalable, locally controlled, local model routing. The most popular ones are various ways of doing small worlds, either explicit small worlds, hidden metric space small world routing, or more explicit small worlds, Kleinberg's hyperbolic routing, where you can use approximate incomplete local information but still get very good routes with very low stretch factors. So this potentially has great scaling. You can have lots of information, but you mostly don't need to know it. You just need to know the stuff that is around you, and it doesn't require summarization. There are more viral models, things that handle very high degrees of mobility, where you're doing stuff that's based on either gradient models, stuff that you should avoid, or percolation models, random walks with learning, so that you can find hubs and good distribution centers. It's all very cool. I think any of it applies to CCN as well as to IP. We're semantically pretty equivalent. It's generally easier to do in CCN than IP for a few reasons that I tried to put here. You don't require convergence in CCN because it's not possible for things to loop. Right? So you don't need a stable topology. You don't need short times to a stable topology, because those exist to prevent looping, and you don't care about looping. The fact that you've got multi-destinations means that you don't need perfect state. So IP requires a certain minimum amount of state because you have to distribute packets along its spanning tree. You can't send packets along the spanning tree and somewhere else, because that might cause a loop, and loops really rapidly take down your network. And you can't send your packets somewhere other than along the spanning tree, because that might cause a black hole. You might send them to somebody who doesn't know where they go. So in IP, at every node, you have to have perfect information. You can't approximate it. CCN, the semantics of a fib entry is this node might have information about the prefix, or information that matches this prefix might be out that face. It's approximate to begin with, and it can be multiple faces. And you can take all of the state and turn it into summarized approximation state, as long as the errors that you're making are false positives. You can send the data anywhere, not just waste bandwidth, as long as one of the places that you send it is the place you should have sent it, right? So in specific, if you want to code your routing tables as a Bloom filter, works perfectly, right? Because Bloom filters only have false positives, they don't have false negatives, right? You're never going to fail to send the data where it should go, but you may, because you compress the state, send it some places where it shouldn't go. That's okay, it'll get discarded because they don't have the data. And you get that out of the multi-point model, sort of for free. It's a consequence of having multi-point delivery. But it means that you can make some, if you care about state and state concentration, you can do explicit state versus bandwidth trade-offs. You can say, oh, I can compress the bejesus out of the state, and all that happens is some fraction of the packets are going to get flooded. They're going to go places where they shouldn't and get discarded. And lastly, if you look at the transport protocol used by routing, it's always a flooding diffusion-based protocol. It has to be, because it's the protocol that's used to create topology, and so it can't rest on topology, right? There would be a recursion problem there. So you have to make routing out of something that doesn't depend on routing, and flooding's all we know that doesn't depend on routing. You can decide it locally, you can implement it locally, it only depends on the information. That means that CCN lets you implement routing protocols directly in the CCN protocol, because its model is what the routing protocols would like to use. So if you want to try any of those things, I'd suggest, hey, do it in CCN. Right? It's just a great discovery vehicle, and if you do it, you get infrastructure protection for free because all the information is secured. You know, it's all signed. I'm not going to talk about any of those. I want to encourage, let's deploy CCN right now today, and you can do that. It's universal middleware model. You want to deploy it over the existing IP routing. Like I said, longest match lookups, it's semantically compatible. It expects the same sort of things that IP expects. If you can do that, if you can dump CCN information into normal internet routing, then you really can deploy it today. And if you can do that, might give you some intuitions on scaling. It really is just the same as IP routing, should have the same scaling properties. So in order to describe that, I need to describe how routing works, because it's black art to many people, probably not to you, but I'll describe it anyway. So I'm just describing link state routing because the other one doesn't really work. Link state, we have nodes that announce their existence via local broadcasts. Across every link they've got, they send out a hello that just says, I exist. So B sends out of each of its links, hello, I'm B. A node that hears that learns that it's adjacent to B, that B can talk to it. So when C hears B's hello, which is local communication on that one link, when C hears it, it floods via a link state announcement what's called an adjacency. So it tells the whole world that there's a unidirectional path from B to C. Same thing happens in the other direction. Right, so C is sending a hello, B floods an adjacency, the whole world learns there's a unidirectional path in the other way, C to B. As soon as the world learns that there's a path both directions, right, this is flooded, so it goes to everybody. So when everybody learns that there's a path from C to B and from B to C, they make a map of the network that includes a link from C to B. For ISIS and OSPF, we require bidirectional connectivity, right? So you have to hear an announcement from each direction, and that causes you to put a link in your map. Every node in link state routing is building a map of the network, right? So everybody's playing this game. Pretty soon you're going to get a map of all the connectivity. right? So you're going to end up with the structure that's drawn here. So that's one part of link state routing. It's the internal part. Each node is creating a map of the entire topology, and it's doing it via these flooded LSAs, which in turn are coming out of the local hellos, which give you the adjacencies. So everybody has this map. The other part is using it. So some external agent, something not part of the cloud, is saying, I'm adjacent to B, and anything that's prefix 192.168, I can reach it. Right? So there's some outside world entity, another routing protocol in the same box, BGP, another version of the IGP. It supplies a prefix that says, at this node, that prefix is reachable. Right? So B takes that prefix and it floods it throughout its network and saying, the prefix 192.168 is reachable via B. You can send to me if you want to get to that. So that's using the map. And again, this is flooded. Everybody learns it. The prefix announcements aren't protocol specific, and they're not topology specific, right? They're information that you want attached to nodes. It can be an IP4 prefix. It can be an IP6 prefix. It can be a time of day. It can be an MPLS label. You really don't care. It's some information that you want associated with a point in the topology. And in the process of moving the protocols from IP4 to IP6, and then trying to put in MPLS and traffic engineering extensions, both OSPF and ISIS really generalize the mechanism for what you can announce at a node, because there were lots of different things they wanted to be able to announce. Prefixes in multiple protocol families, characteristics of links, all of those things could be distributed. They could be encoded in what's called a TLV, type length value. You get to choose the types arbitrarily. You say how many bytes of data there is, a code for the type, how many bytes of data, and then that many bytes of opaque data. And that can be flooded throughout the entire topology. It's attached to a particular node that originates it. So model is you have CCN content repositories that have certain prefixes they handle. They learn about that via internal CCN protocols called registrations. There's a registration agent that talks to routing, to a border router, and says, these content labels are available next to you. Right. So adjacent to B is some set of name prefixes, CCN prefixes. B takes those prefixes, floods them via the IGP flooding mechanism, the TLV mechanism, floods them throughout the topology. Routers that don't speak CCN, the guys that are only single line, they discard the information. They say, it doesn't apply to me. Guys that do speak CCN, they use it to build a fib. So you hear an announcement from A about the prefixes it handles. This is the fib that you build from those announcements. You hear an announcement from B about the prefixes it handles. It makes that fib entry. It doesn't matter how you learn it. Right? You're getting the labels bound to points in the topology via the IGP flooding mechanism. You're using it as a transport. You construct a fib because you know the topology and you know where the labels are. You find the closest CCN capable entity in the direction of the prefix, and that's what you put in the fib. Right? So here, the closest CCN capable entities are the originators, A and B. If you upgrade C so it speaks CCN, all those fib entries turn into Cs, right? Because the way that you would get to A or B via a CCN capable path is via C. So you can dump CCN prefixes because they're semantically compatible with IP and because the routing protocols are sufficiently general. You can jump them straight into your existing IGPs. You can dump them straight into BGP the same way. It had the same TLV mechanism for the same reason. It's unfortunately not a link state protocol. It's a modified distance vector protocol, and it tends to hide a lot of information. So I'm not sure that you want to do it that way. What we're doing currently in CCN is using the DNS in order to handle the interdomain case. And I'm not going to talk about that, but can talk about it offline. I want to talk a little bit about problems with the IP routing model that you don't have with the CCN model. So I did this picture about how the data is summarized, reduce it to just the node link diagram. Right, so these were the subnets, the net, the foreign nets. That's the connectivity. The problem is it's got a lot of double edges. It's got a lot of loops. And IP can't deal with that. So you have to impose a topology on that. After we've done the routing computation, we end up with a spanning tree. So a bunch of the edges have to vanish. They have to go away. Even though that's capacity that we could send bits over, we can't use it. We're talking about a topology that has to span the whole world, and there has to be a lot of consistency in that topology. There's certain levels of churn where you can't send data if the topology is still converging. And core parts of the topology, if they change, it can take a long time to reconverge, to reestablish that topology. So there's lots of times when you may not be able to send data. And those times can be triggered by very small things. A couple of years ago, an ISP in India, a really tiny ISDN ISP in India, misconfigured their prefixes. And they were injecting via BGP 100,000 withdrawals, announced withdrawals an hour. And that caused BGP boxes all over the world to fall over. Right? Cisco just couldn't handle that rate. TCP could move the bits, but the BGP and the mesh topology that's implied by BGP, it just couldn't handle that traffic rate. BGP router falls over, then you lose the high level, the tier 1 adjacencies, right? So this churn at the far edge of the network is almost inconsequential. It turns into churn in the core of the network, and it took down the internet. Right? There were large parts of the Pacific Rim that weren't reachable, and they weren't reachable for a couple of days. Cisco sent out an emergency patch. People were filtering out. They identified who was doing this. They were filtering out the traffic, but they had to do that manually. And because we require this topology to communicate, we're dead in the water. So there are global effects for local actions. And it doesn't have to be a big player's local action. It could be anybody's local action. And that's that you get global constraints on the forwarding because you have to be on the spanning tree. And for the intermediate guys, they don't get a choice. Right? Because in IP there's only one path between any 2 points. When you get a packet to a non-local destination address, you have to forward it. It doesn't matter if you look at it and you say, oh, I don't want to handle this, right? That's not my customer, or I don't trust this packet, or I'm really at my quota. You are on the path, right? If you got it, somebody thought that you were on the only way to get between point A and point B. And if you throw the packet away, then you've made a black hole. Those two nodes can't communicate. So you end up, because you have to be part of this global forwarding structure, the single spanning tree, you have global constraints on your local routing decision. If you do CCN, you don't need topology. At best, it's a hint. It saves you some bandwidth. Right? You can use any or all your links, and you can use them all the time. You don't need it because the content model suppresses duplicates. There's nothing that can loop. Data gets extinguished immediately if it goes around a loop. There's something called a nonce. There's an identifier that goes in the interest. If they go around a loop, they get extinguished. The data bandwidth is going to be a theoretical min, right? You get the data from the closest point. If you do that by flooding interests, there's going to be some off-path, off-closest point copies that get sent to you and that get extinguished because they're duplicates. If you have topology, then you don't send those off-path interests. The amount of win that you get from doing that is a really small factor. It's some fraction of the average degree times the diameter of the net. Those copies would tend to go off and then remerge again unless the data is really in disjoint places. And so what you win is those little splits. And if you actually compute it, it's a tiny number. So you actually get CCN to work best if it's got crummy topology, approximate topology, and you do something that we call performance-based interest tree expression. I've only got 10 minutes to... And I'm losing my mic? Okay. I want to go briefly into transport. It's the last big issue, and I think I can skip the rest of the slides. We've got this tree-based content model, and you're asking for things an item at a time, right? How do you get big stuff? How do you say what you want? That's the fundamental problem of transport. It's easy in a stream-oriented transport because basically you're enumerating a byte stream, right? And a line is totally ordered, right? So if you can say what you've got, you can say the mark between what you've got, that's what you want is everything after that mark. And that's what TCP does. That's what a TCP sequence number is. So there's some point that an ACK identifies that's everything that you've got. Everything after the ACK, all the bytes higher in sequence order, are stuff that you want. And there's another parameter called the window that's how much you allow to be in transit. So how many of those bytes the sender is allowed to send. It's a really compact state. It's really easy to robustly move data. How do you do the same thing with this tree-structured CCN namespace? Well, you take advantage of the fact that the one data structure, in addition to a line, that you can totally order as a tree. You can't totally order a graph. You can't totally order any two-dimensional or higher structure, but you can totally order a tree. In fact, many different ways. We order it in pre-order, lexicographic order. And that means that these names have a total ordering, therefore I can say what I want relative to what I have. And that specifies a particular path through the tree. And I put the conventions down here. The tree is lexically ordered. If you don't give a relationship, what you're asking for is the leftmost child going down the tree. So you're going to follow the branch. I probably have this on a picture, and I should do the picture. So if I give that name, slides from a talk, and I want to ask for the highest version, but I don't know what the highest version is. Right? So I ask for the base name of the talk, not including the version number, and I ask for the rightmost child of that base name. Version numbers are ascending integers, so the rightmost child is the highest version. That's the application convention. So asking for the rightmost child gives me the most recent version, and I don't need to know what it is. And then from the rightmost child, the default convention is follow down the leftmost child, so its leftmost child is block 0 in that piece of content. Right? So that name is going to give me the first block of the most recent version. And I don't have to know anything more than the base name. If I want the next version, it's pub/sub, I'm trying to find that a new version has been created. So I asked for the version after version 2. So it's the rightmost sibling of version 2. There isn't one. And you get back, if you talk to something that's authoritative or repository for that content, it's going to give you back a NAC that says, doesn't exist yet. I know, and it doesn't exist yet. If you don't get to an authoritative repository, it's going to time out. If I've got chunk S1 and I want some chunk after it, so it's the TCP example, I've got everything S1 and before, and I want something after it, I ask for that name. I give the name of the most recent thing I got, and that implicitly, because of the resolution rules, is the next thing, anything afterwards. So the names are what you use for transport state. Basically, you get a packet in the default case, and you turn the name in that packet into your next interest. And that interest is asking for the thing after what you've got. Content storage. So there's roughly 10 million people that read the New York Times online in the US. And they all pull a copy from the nytimes.com. It's not Akamai's because NY Times wants to tell its advertisers exactly how many people read it. How would you do that with CCN? Well, so the model is a sort of recursive model. Client announces its interest. The interest percolates back to NY Times because nobody along the path has it. NY Times sends the data. As it's going back down to the client, it's remembered in the content store of all of the routers along that branch. Right? So the data is both delivered to the client, but everybody who's marked in blue has a copy. Client 2 asks for the same data. So its interest propagates up. As soon as it hits a place where the content exists, the interest matches the content store and is sent from that point. So basically you add the branch from the client to where the data already is. So you're making a content distribution network. You're doing it dynamically. It's based on the interest. Right? It's a distribution network that's specialized to that particular set of interests that is only going to go where there's interest. You can prove that any piece of data is going to take at most one trip across any given link, because after it's taken a trip, it's in the downstream content store and it's going to be satisfied out of the content store, so you don't need to pull it across the link again. That's optimal, right? You can't do a delivery network that uses less bandwidth than that. Because in this model, and in most of the models, you're distributing along a source tree, right? There's a root that has the content and it's going out to all the consumers of that content. All of the mass of a tree is at its leaves. Right? You sort of see it in this picture, but it doesn't have to be a binary tree. In general, the nature of a tree is the mass is down at the leaves. What that means is there are lots of copies that get seeded very close to the consumers, which means that the average latency, how far you have to go to get your copy, is very low because the data very rapidly percolates from the root of the tree deeper into it, which means closer to the consumers. And none of these replicas announce the replicas. The fact that we're putting the data in our content store, to be useful, it doesn't require that we say via routing that we've got the data. The way that the data is found is because we're on the path to the source of the data, it's discovered from the routing that defines the distribution tree. This is the same model that's used in things like CBT multicast, core-based trees, that you don't have to put state everywhere. You can have very high-level state, things that defines repositories. That induces trees, which can be then used to control the distribution of replicas and let you use those replicas efficiently. And the efficiency is described there. Minimum bandwidth, minimum latency, minimum link use. So you make a close to optimal CDN with no control traffic automatically. And it's specialized because it's done on each particular data item. The distribution network is specialized per those data items. So we've got an implementation of CCN running. We're planning to do a GPL'd open source release of it, of the core of it, which is what we've got running, in September. I'm not sure when in September, but it's going to be before the last day of September, this September. The people that do real work are working on it while I'm here enjoying myself. We've done some measurements of that implementation. Here's some data. This is a comparison of the bulk data transfer performance of CCN versus TCP. It's not just a request response protocol. I mean, you can embed TCP IP in it. You would like it to have the same performance. So here we're varying the window size for TCP. That's the x-axis, the pipeline size. And we're verifying the number of simultaneous interests you can have in process for CCN, which is the same parameter, right? How many unsatisfied interests you can have outstanding. And we're varying it from 1 up to about 50. And the numbers there are packets to make them directly comparable. So You can see for TCP it runs stop and wait when it's only got one packet. It increases linearly as you give it more packets. This is a local test, so there's no transit delay. It's all store and forward delays, which is why that goes up so steeply and why it's really flat. Right? It's why it's not round. And then we saturate at the link bandwidth, which is 100 megabit per second. CCN, this is TCP's a kernel level implementation that's been continuously tuned for 20 years. It's pretty good. CCN is a task level implementation, which we've had running for a couple of weeks. It's pretty bad. So the leading edge is really pretty grim there. It's a big pipe because you're going from application into the kernel, out to another application, back into the kernel. You do that 2 times per hop. And so a lot more store and forward delays, a lot more rise time, but it goes up and it flattens out. We get an asymptotic throughput that you can read from the asymptotes the relative efficiency of these protocols. TCP is 11, the app bandwidth, which is what we're displaying here, is 11% down from the link bandwidth. That's the size of the headers, the Ethernet header and the 40 byte TCP IP header. Right? The CCN is encapsulated in UDP, so it's got the same Ethernet and IP headers on it, plus a CCN header. Right? So its bandwidth, it can't do any better than TCP is doing, and it does 23% worth. That's basically the size of the name and the size of the SHA-256. Right? So our name is as big as a TCP header, and our SHA-256 is as big as a TCP header, so we've got exactly twice the overhead. We get to within the overhead, we get the same asymptotic throughput. We saturate the wire, right? We're running flat. At the wire, we're running 100 megabits per second. We're down 20% in the throughput because it's not an apples for apples comparison. We do security and TCP doesn't. Right? And basically the factor of 2 difference is the security overhead. Things change a lot if you look at a sharing test. So here we were distributing a video to 4 clients, and a YouTube video, do it via TCP, and you do it via CCN. TCP, and we're doing this over a 10 megabit Ethernet. So it's a bottleneck link, slow bottleneck link. In TCP, each client pulls down a separate copy, so as you add more clients, this is measuring the time until the last guy gets the video, so it's the time to completion for all 4. For TCP, the time to completion goes up linearly as you add the clients because they're all sharing the same bandwidth, and so as you add a new client, you're having the bandwidth for each of the others. For CCN, number of clients doesn't matter because they all share the same, broadcast protocols. They all share the same copy. So irrespective of the number of copies, you get the same performance. I want to say this one last thing about mobility management, and then I'm over my time. So in CCN, the issues of mobility management are very much easier. I mean, they're a reality in the modern world. They're hard to deal with. They're way harder to deal with in IP. The core one, in IP, who you're talking to matters. And so when that changes, you have to somehow paste over the fact that it's changed. And use mobile IP or some other tunneling mechanism to do that. You have to bind a host identity. In CCN, it doesn't matter who you're talking to. It matters who you're talking about. And so if who you're talking to changes, you don't care. You didn't care to begin with. You don't know. So there's a level of mobility management, the session preservation, that simply doesn't exist because you're dealing at the content level, and that's immune to mobility. When I move from here to there, I still want the same stuff. Right? So I just can keep asking. There's another issue of mobility management that has to do with the connection-oriented, you ask for, say, a YouTube video. That's the granularity at which you can request data, and then you get the whole thing. It's because the segmentation is a transport level abstraction, not a network level abstraction. So getting data is all or nothing at very large levels. So when you're pulling down a YouTube video and you move to a different place, the data that's coming towards you, you have to somehow revector to that different place. And you don't want to waste a lot of bandwidth putting it in the wrong place. It constrains the way that you construct tunnels and how dynamically you want to construct tunnels. And you have to predict where you're going to be in order to correctly move the data and not send too much of it to the wrong place. It's because you're dealing with very large units. CCN, the segmentation is done at the lowest level, and you ask for a packet at a time. So it doesn't matter if the original piece of content was 60 gigabytes, you're getting it a kilobyte at a time. And if you're talking to something upstream that says, we've got a 2-packet bandwidth delay product, you give me 1,000 outstanding interests, I'll forward 2, because we've got a 2-packet bandwidth delay product, and you only need 2 to fill the pipe. Right? So you don't have a lot of data that's coming at you. And if you move, you haven't made a very big mistake. And because that data is being cached all along the path, even if it goes to the place where you've been, it also went to the guy upstream of him, and that's a copy that you can get in the new place that you are. Right? You can take advantage of the locality, which means that you can do very efficient mobile distribution being very stupid. You don't have to predict where you are, you don't have to know where you're going, you don't have to know where the infrastructure is, because you're not making a bunch of big mistakes that you then need to fix. And lastly, because you don't have to worry about looping, you can use all your links and you can use them all simultaneously. So if you're trying to figure out of a set of carrier wireless, infrastructure wireless, point-to-point connections, Bluetooth, figure out what works to get a piece of data, the answer is try them all. Something's going to respond. I'm going to see the response because interest and data are always paired. There's no unidirectional communication in CCN. There's always a pairing. So you can try experiments and you can always measure the results. And you can condition your future behavior based on measured results. So the answer for a lot of the mobility management is try it, conditional on policy, like I don't want to charge my 3G link, I don't want to use my 3G link any more than I have to because I have to pay a lot for the sucker, but everything else, try it. If it works, use it. And I will know unambiguously if it works because I can measure it. I send my interest, I get my data. I'm going to skip over this, I hope. Come on, I hate builds. Go away. This is our CCN protocol stack. We take the IP model, as Norbert was saying yesterday, the waste, IP, that narrow waste in the stack, has been tremendously valuable. It let us evolve what's below it and above it in many different dimensions. New services, new applications, create things like the web, create things like VoIP. But there may be other things that are equally as valuable for the waste. We think that little chunks of content in the very specific, what I talked about for CCN content, signed name pieces of data, we think that would be a really appropriate waste for the world as it is today. You need to put 2 new layers around that. One we call the strategy layer, and it's basically the mobility management layer. It has to be in the stack because the world today is lots of ways to communicate. And you need to figure out dynamically, almost on a packet by packet basis, what's the best way to communicate. And that needs to be in the stack. And your stack needs to be engineered so you can use that information. The other is there needs to be a security layer. I mean, trust is just too important. Provenance is just too important. The network and communication is too much a part of our lives. And that has to be in the stack. And at least the identity part can't be optional. You have to be able to do the signing. Other than that, it looks pretty much like an IP stack. And it's as simple, roughly the same performance, I believe. And with that, I am done, except for questions. I'm over my time. Do we have time? Yeah.
The question in 70 number slides. 70 number slides.
Go back to 70. Let me see if I can figure out how to do it. This one?
No. Oh, okay. Actually, you told that that is if someone gets the data from one of the nodes that is far away, then another node that is near to this the node that already used the data, this node will be able to take the data very easily from this node. But and last some other slides before you told that is in every node the address of the content is stored. Is this the address of the content or the content itself?
It's the content itself,
Yeah,
and its name.
A lot of waste of resource because of wastage of resource.
It's the resource. So if you're doing stat muxing, you've got to have a buffer. And all CCN says is there's a smarter way to use that buffer than to use it for queues. It's a memory. Treat it as a memory. Treat it as an addressable entity. We've got the addresses, they're the content names. And so when a packet lands in a buffer, remember that. So it's no waste of memory. It's the packet landed in that memory. It lands there for IP. It lands there for CCN. Right? The buffer has to exist. CCN doesn't require any more buffer than IP does. IP, there's a certain minimum buffer that you have to handle the statistical variation. CCN requires basically the same amount for different reasons, but it's basically the same amount. And you're going to get the data because of the dynamics of the protocol and IP. You have to throw it away. There's no way that you can use it again. And so it ends up being discarded. But it was a valid copy of the data. If the protocol were designed so that you could use it again in IP, you wouldn't put it in a queue. You would save it and you would use it again. But we can't. In CCN, it's designed so that the data is reusable. It's because you address things via data, not via host associations or transient associations like a TCP 5-tuple. And because of that, because of the reuse, same memory, no more is required, but we can use it in a way that facilitates reuse. And that doesn't cost you anything, right? If the data is never reused, you don't pay any more with CCN than you would with TCP, modulo bigger headers, right? So slightly lower efficiency. But CCN is as efficient as TCP for data that's only used once, and if you use more than once, it's exponentially more efficiency, right? The 10 million copies of the New York Times, one trip across the link, so you get huge bandwidth reductions.
Wonderful talk, thank you. My question is the following. I'm trying to understand what kind of assumption you make for the progression of technology for your model to be really adopted and work. So you talked about cheap memory, because you store a lot of information on it. You talked about the progress in hashing, understanding hashing better. Are there other key technologies or key discoveries which you base essentially your model on?
No, we're not even basing it on. If you look through the measurements, if you deploy CCN today with the routers that you have today, it's a win, because you don't. If there's no sharing, right? If the traffic pattern is exactly conversational traffic with no reuse, at worst you pay an additional 10% in the overhead, but you get much higher data integrity. If there's any sharing whatsoever, then you win by the amount of sharing. And for highly replicated content, for things like YouTube, it could be a really big win. So there's a benefit with no technology changes. Likely changes of the technology are cheap memory means you could remember a lot more. That's of no value to IP. In fact, it's a detriment. That can only let you make the queues bigger, but they're already too big. You really want to go the other direction. But with CCN, it's a huge win. It means you could remember more. It means more opportunities for sharing, which means less bandwidth use, because there's a direct trade-off between memory and bandwidth in CCN, not in IP. If you can apply the hashing algorithms in your forwarding decision, you can handle a lot more diversity in the data. So you really need data creation processes that have the same homogeneity as the IP processes, in order to get the same state growth for CCN. That means that content really needs to have repositories at institutions so that you find it one place or a couple places. If you can have a lot more memory available for FIBs, then the content can be at a lot more places. You can start to apply the much more distributed, much more autonomous routing algorithms like small worlds, things that right now are done in peer-to-peer networks, but really inefficiently because they can take advantage of locality. You can start to use them in CCN, get really good locality, but get lots of autonomy, where content can now be created by individuals and presented by individuals, and you don't have an issue with the state burden of that you have the memory and the scalable lookup algorithms to deal with it. That's a research topic, and at this point all I can do is wave my hands, but I wave them with some confidence and would welcome anybody who wants to look in that area. Yes?
You only showed the advantage over CCN over IP. There must be some disadvantage, no?
No.
IP's there.
Oh yeah, I'm not saying get rid of IP. It's a wonderful thing. It's just an incredible engineering achievement, and it's, I think, an unmatched engineering achievement. And we're copying it. We're using as much of it as we can. And you're going to deploy CCN over IP, just like IP was deployed over the telephone network. And Vint never said, I want to replace the telephone network. He wanted to do something new. CCN's something new. It does very well, better than TCP can do.
Yeah, maybe one more question, because then we have to get to lunch. So.
Does the content expire, and if not, other content is stored independently in a node?
I'm sorry, my hearing is very... Oh, yes. So one of the things that was on a slide I had to skip was part of the annotation in a data packet, part of the metadata, is what we call a stale time. And its semantics is that much time after the arrival of the packet, it should be marked stale. There's a bit in the interest, in the CCN selector bit, that says whether or not you will accept stale data. And by default, you don't accept stale data. So what generally happens is the content creator sets a stale time that's defined relative to their production process, right? So New York Times sets a stale time of a few hours. The data goes out. After a few hours, it vanishes from the caches, which causes interest to come up, which solicit new data. Because at most one interest goes up, irrespective of how many people are asking, right? They all get aggregated as you're going up the source tree, and one piece of data comes down. You don't need to set long stale times to control your incoming traffic for coherence. It doesn't matter how many people are interested, you're going to get one interest per whatever the stale time is. And so it's not a traffic management issue, except in aggregate. And you want to give a good customer experience, you want to let the replicas live as long as they can because they're lower latency if you satisfy from the replicas.
I'm very sorry that I have to sort of cut off the discussion here, but Van will be here tomorrow, so you have another couple of coffee breaks, social event, etc. And also there's a small group discussion with some partners from Forward and Chianti tomorrow after the coffee break, so if you want to join that, please contact me. Okay, so please try to be back as close to 2 o'clock as you can to